Research Chair in the Foundations of Physics. And since 2017, he has been a group leader at the Institute for Quantum Optics and Quantum Information in Vienna. So today he'll be speaking on black boxes in space and time, semi-device independent information processing via representation theory. So welcome and over to you, Marcus.
Okay, thanks very much for the nice introduction and for inviting me. By the way, can you still hear me? Does that work well?
Yeah.
Okay, great. Needless to say, it would have been much nicer to be in Mohali in person. So this is now the second best thing somehow to have an online talk at least. So I will talk about black boxes in space and time. And this is about a paper that just came out this year with Andy and Marius here in my group. And here's a little overview on my talk. So I will begin with the general framework of these, what I call sometimes space-time boxes. So these are black boxes, like in the picture here, spell scenario, but boxes that somehow live in space and time and respond to space-time symmetries in a certain way. That's the main idea. So the first part will introduce a general framework. In the second part, I will show you that this framework allows for a couple of foundational insights about quantum correlations, for example. In the third part, I will talk about the idea to have new information processing protocols using this framework. And I will also show a kind of proof of principle how this can be made to work. The fourth part will really just be a single slide with an idea that perhaps one can use all this for new experimental tests of quantum theory. All right, so let's see. Okay, so let's go to the first part. So what is black box quantum information? So let me start by telling you a few things that almost everybody of you knows already very well, just as a recapitulation somehow. So one scenario in where black boxes appear is just a Bell scenario. You have Alice and Bob, two parties that are space-like separated. They share some resource, which could be an entangled quantum state, for example. And then they can locally in their laboratories choose inputs. Quantum theory, these inputs could be choices of measurement directions, for example. And they will then find outputs A and B, outcomes of measurements. And formulating this scenario in terms of black boxes means that we're not making any assumptions about what's actually happening in the boxes in the laboratories, but we're really only looking at the statistics, so at the outcome probabilities P of A, B given settings X and Y. Now, certainly if we have classical physics or classical probability theory, then this particular situation with its causal scenario would be formalized in this way here. We would say that, well, we have a scenario where we have a distributed randomness, some hidden variables, as they're sometimes called lambda, that have been distributed to Alice and Bob in the past. And then the conditional probability P of A, B given X, Y is basically just given by the chain rule. So we have to sum over the lambdas, and then we get an expression like that here, where we have just local response functions, PA and PB for Alice and Bob, basically. In quantum physics, the resource would just be a quantum state. It could be an entangled quantum state, for example. And the probabilities would then be given by the Born rule, according to the state that has been shared by Alice and Bob, and some local measurement operators or POVM elements. And in both situations, we have the no signaling conditions. So it is true that Bob cannot certainly not send information to Alice simply by choosing his measurements, and vice versa. Alice also cannot send information just by choosing her input X. And this is formulated by these conditions here. So the local probability, for example, of Alice's outcome, if I marginalize over Bob's outcome, this is really independent of Bob's setting Y. And similarly, if A and B are interchanged. So despite the similarity, as all of you I think know very well, of course, is that the correlations, these probability tables, P of A, B given X, Y, that we can see in quantum physics are more general than those that we can see in classical physics. And here's a picture how this is often depicted. So if you just say what are all the possible behaviors or probability tables that satisfy the no signaling conditions, then you'll find a very large polytope, which is the no signaling polytope. The set of possible quantum correlations is a subset of this polytope. And an even smaller subset is the set of classical correlations. And the fact that there are more quantum than classical correlations is certified, for example, by a violation of Bell inequalities. Now, why should we study such correlations? Well, the first reason is just foundational. So we can ask, well, it seems that nature allows, well, we know that nature allows more general than classical correlations, but why just the quantum correlations Q, and why not other correlations? So there has been a lot of work on trying to find, say, physical principles that tell us, in some sense, why we have quantum correlations in our world, without assuming, for example, the Hilbert space formalism, of course, in the first place. But there's also an applied side to that. So we can basically have something like device-independent protocols. So in this black box picture, if we do not make any assumptions on what our devices are doing, it is still possible, for example, to perform randomness amplification or to create secure cryptographic keys just by relying on the no signaling principle and on the violation of a Bell inequality. So certainly the Bell scenario is not the only one in which this kind of black box picture appears. Another scenario we'll get back to also later is a semi-device independent scenarios, like, for example, a prepare and measure scenario. So this would be a situation, for example, where Alice on the left would press a button and then choose an input X, and then you get a quantum state is prepared, rho X. This quantum state is sent to Bob, and then Bob performs a measurement on it. So you have actually quantum states that are transmitted from Alice to Bob. And this is not fully device independent. You need to make extra assumptions in addition to no signaling or just the statistics that you see. But this, when you do this, for example, by having a dimension bound on your system rho X, this also allows you to perform useful protocols. Okay, now what about these single black boxes? So typically how we think of it is we have an input and an output and a conditional probability like P of A given X. And typically in quantum information theory, both inputs and outputs are typically taken to be abstract labels. The input could be 0 or 1, basically a bit, and the output is sometimes denoted just -1 or +1. Or perhaps there's a larger discrete set, but in any case, these are like usually abstract labels. However, you can ask, well, what if there's more structure to that situation? So what, for example, if the inputs or perhaps the outputs or both are spatio-temporal quantities in some sense? So for example, maybe you choose your input not by choosing a bit, but by setting an angle in a polarizer in a certain angle, or by setting a magnetic field in a certain direction, right? So this is very well motivated to ask whether we can somehow consider this extra structure for these boxes, because I would argue that in many actual experimental settings, this is what we have. We're not really choosing abstract inputs, but we're choosing some kind of spatio-temporal input to our experiment. Also, when asking this question about how can the statistics of such a box be impacted if our input is of that form, will allow us to study in an interesting way some of the interplay of probability on the one hand and of space and time on the other hand, and do so under minimal assumptions. And the motivation to this comes also to some extent from the history of physics. So the success of quantum field theory is, in some sense, can be traced back to the idea that we want to combine the principles of quantum theory, which tell us about detector click probabilities, basically, and space-time physics, like Lorentz invariance. And so why not do this or something similar in the context of black box quantum information? Then, then the idea is also maybe if we have these additional spatio-temporal symmetries, perhaps they can be made of use, they can really be useful in certain protocols. And we will see that later on, that this can sometimes be the case. And then a more foundational question would be, well, how could, in fact, possible beyond quantum physics, perhaps one with stronger than quantum correlations, how could that fit into space and time? All right, so how do we now address these questions? So what kind of formalism are we proposing here? So let's look at a simple example first. The Stern-Gerlach experiment, a very simple example, where you see you prepare a source, and then you have a magnetic field, and then you get one of two outcomes, plus or minus 1. Now, the magnetic field is a directional vector, so it tells you it's like a vector in the direction of inhomogeneity of the magnetic field. And what you can study in such a situation is the probability of the outcome A, which is -1 or +1, given your input x. And x is now a unit vector which tells you where the magnetic field on its inhomogeneity is actually pointing, basically. Right, so how would we formalize this in a general framework? Well, what we do is we begin by saying, let's talk not about the direction itself, but about the symmetry groups that are involved in the setup. So the idea is that we have a magnet with a kind of default direction of the inhomogeneity of the field, which is a vector x0. Perhaps that's always pointing in the x direction. And then we can choose to perform a rotation of our setup. So we can choose to rotate the magnet by a spatial rotation R, which is an element of the symmetry group, SO3 in this case. So we think somehow that we have our experiment, but there's also an external reference frame with respect to which we can apply a symmetry transformation to our experiment. So if we apply this rotation R to our initial default vector x0, we rotate magnetic field somewhere else, and this is the direction x. Now, let's do this one step more abstract. So what we see is certainly that some rotations do not have any impact at all. So when you perform a rotation, that's an element of the stabilizer subgroup of our default direction. So R of x0 is just x0. We're really rotating in the direction of x0. Then we have the same input. So we have, in this case, a subgroup of our symmetry group, which tells us that nothing changes. And then we can see the inputs as a kind of manifold. So this is a homogeneous space. It's basically our symmetry group, SO3, divided by the stabilizer subgroup, SO2, which really gives you the unit sphere S2, as we claimed in the beginning. So in general, we would say that we have a box, and the inputs to the box are now elements of some homogeneous space. We have a group G, a symmetry group, and a stabilizer subgroup H. So in this case, and this is what we've done in this paper, just the abstract box with the abstract inputs and outputs is replaced by a box of that form here. And we've just seen an example. In a Stein-Gerlach experiment, the group would be SO3, the stabilizer subgroup would be SO2, and so the set of inputs would then be a unit vector. But you can think of a polarizer, for example, where you send a beam, you rotate your polarizer in a certain angle, and then you get a click or you don't get a click, which could be plus or minus 1. In this case, your symmetry group itself would be SO2, just the rotations around the beam axis. The stabilizer subgroup would be trivial, like no other additional symmetries here. And so your input would be an element of SO2, which can be parameterized by an angle alpha. Or you can think of a scenario where basically you send, say, a pulse of a certain duration, or you wait a certain time t in which you involve your closed system, and then you record whether you had a click in the meantime or not. So this can be formalized here as well, either as a symmetry group or a symmetry semi-group, where in this case, a symmetry group would be just the group of time translations R, and then your input to the box would be a time t, which is just a real number. Okay. Now, what can we now say when we have such a box? Well, one thing we have to say is that since we can perform symmetry transformations to the box, it's certainly the case that the outcome probabilities must respond to this in a certain consistent way. For example, if you prepare a box at random by tossing a coin or so, then there should be an interplay between this convex mixture of boxes and the way that your symmetry group acts on the box. This allows you to show, under some assumptions, this kind of theorem here, perhaps not very surprising, but indeed very useful. So probabilistic consistency alone implies that the probability table for such a box must be a linear combination of matrix entries of some group representation of the symmetry group over the real numbers. Now, we are used to this within quantum mechanics. In quantum mechanics, we would say, well, sure, we have a unitary representation of the rotation group. And when I use that and the Born rule, then somehow these, I get a linear combination of the matrix entries of the representation. But here this is true more generally. So this can be shown without assuming quantum mechanics, basically, just in a very general framework. So let's look at an example. So here's, for example, a Bell scenario where we think of Alice and Box as choosing their inputs by an SO2 rotation. So you can think of this as a symmetry group SO2 times SO2 of two independent rotations that determine your bipartite box on A and B. So what do we know about representations of this group? A theorem tells us that we have to look at those. Well, they are basically all of that form. They are direct sums of these 2x2 matrices, like cosine of m alpha minus n beta and so on. Yeah. So this is not too difficult to see that these are representations of SO2 times SO2. Now what this theorem says now is that the probability tables that Alice and Bob must measure must then be given by combinations of entries of these matrices. So this tells us that the probabilities of AB given alpha and beta can be written in that form, basically. So it's basically a bunch of sines and cosines and some coefficients. And certainly the coefficients must be of a form that gives you positive probabilities, for example, and they're non-negative probabilities. But we get that form here. Now, just two examples to get a bit of a feeling. Maybe we're not interested in the full probability table, but just the correlators. So this means that we look at the outcomes A and B and multiply both of them and take the expectation value. Then one example would really just be a two-photon singlet state, where Alice and Bob basically measure photon polarization on a singlet state. They would find a correlation function as a minus cosine of 2 alpha minus beta, for example. So this very well fits this expression here. And but you can also think of something like a pair of science fiction polarizers, where the correlation function is given by something like that, a trigonometric polynomial, which looks quite innocent. This would be a correlation that satisfies the no signaling principle, that gives you valid probabilities, and where basically only the difference of the angles between Alice and Bob determine what you see. But it turns out that this correlation function cannot be satisfied in quantum theory, even though it responds to symmetries in some sense in a consistent way. You can see this by seeing that that would violate the Bell CH-SH inequality by more than any quantum state, for example. So here you get also a picture very similar to the old one, where you say, well, fixing such a group and looking at the possible correlations, you get a classical and a quantum and a no signaling set. And the quantum set is really just a subset of all possible combinations you can think of. All right. Now, one thing that we addressed, a kind of foundational question that we addressed in our paper is the following. So usually, when you say, here's a non-classical correlation, what you have to do is you have to somehow show that the correlations are strong enough. So for example, that I get over something like 3/4 and some winning probability of some game or so. Now, could it be, that's what we asked first, could it be that here we can do something else? Perhaps it's sufficient to just look at the correlation function and just see what sine and cosine terms appear. So instead of the strength of correlations, can we perhaps just look at the form of the correlations and already rule out a classical explanation of such correlations? So think, for example, of correlation function that we measure that's a trigonometric polynomial. For simplicity, let's say the constant coefficient is 0. Can it be classical or not? Well, the answer is to this question is unfortunately no. So the form of the correlations does not allow one to deduce non-locality, because as long as the correlations, which could be between -1 and +1, are close enough to 0, then these correlation functions always admit of a local hidden variable model, no matter what kind of sine and cosine terms you collect. And that's likely true for other kinds of groups as well. And you can show this by basically constructing local hidden variable models that live on the group in some sense. So the form of correlations does not directly give you non-locality, as we might have hoped in the beginning. But you can say something else, which is interesting perhaps. So let me now go to some kind of foundational insights in this framework. You can make some assumptions on the response of these devices to symmetries and then deduce that the correlations must be quantum. So think of a scenario like this again. It could be two polarizers, in which case Alice and Bob could have two SO2 rotations. But instead now think of Alice and Bob living in d-dimensional space, where d could be 2, 3, 4, or whatever. And they rotate a vector around in their laboratory, which will be their input to the box. Now let's make two example assumptions here, two kind of innocent assumptions. The first assumption would be somehow phrased in physics language, somehow like the probabilities transform like a vector or something like this. So would mean that the outcome probabilities P of AB, given the local rotations R and S that Alice and Bob are doing, let's assume that they transform according to the fundamental representation of SOD. So what this means is that, what I call this is that they transform locally fundamentally, so that the probability is somehow linear in these rotation matrices. So this is in some sense the simplest possible behavior under space-time symmetries that you can think of. Let's make one additional assumption. Let's assume that these devices are locally unbiased. And with that, I mean that basically plus and minus one, your outcomes, appear on average with equal frequency. So when you rotate Alice's box around in all directions, then on average, you will find outcome 0. So you can think of this geometrically as, for example, following from saying, oh, if I reflect my vector in the other direction, then I get a minus sign on my outcome or something like this. So this is another symmetry condition. And then one can show that this alone is sufficient to guarantee that you have quantum correlations in such an experiment. So in any world, whatever world that is, one where quantum theory perhaps does not hold, but some other theory, but where these assumptions hold, Alice and Bob must see quantum correlations. So in fact, you can say this more generally, and you can use this as to characterize the 2-2-2 quantum correlations exactly. So 2-2-2 means if you look at the quantum correlations for two parties, Alice and Bob, which each have two settings and two outcomes, and it turns out that this set of correlations corresponds exactly to those that can be obtained via such SOD times SOD boxes, where D is at most 2, at least 2. If you assume that they transform locally fundamentally in the sense and that they're locally unbiased, and you give them only two possible settings. Also, you may give them shared randomness in addition. So this characterizes this quantum set somehow inside the no signaling set. So you can think of this as perhaps some kind of fundamental relation between the structure of quantum theory and space-time, in some sense. Now, let's look again at the dimension 2 case, where we really have two polarizers. And we have already shown that you can write the probability table in that form here. So it's a bunch of sines and cosines coming from different representations of the group. And here the sum goes from 0 to j, or 2j. And in some sense, j is a representation label. It's like a spin label of the highest representation that you can have with which your devices respond. Now, what I called transforming locally fundamentally in this language is nothing but a condition that this j can be at most 1/2 in some sense. So what the previous result tells you is that if we look at these abstract boxes and then we bound the representation label in some sense, then this can really constrain the correlations that you can see in an experiment. So in some sense, this amounts to making an assumption of how the devices respond to spatiotemporal symmetry transformations. And in some cases, we may have physically well-motivated beliefs about what these devices are doing. And now the idea is to actually use this in protocols. So not just to get an interesting insight on the structure of quantum correlations, but really to perhaps get new protocols for quantum information processing. And now this will be the third part of my talk. So in a Bell scenario, we really only need to assume the no signaling principle and nothing else. So this is really a device-independent setting. And this device-independent setting can be used for randomness expansion or for cryptography without having any trust in our devices. There's, again, this, as I said before, a setting which can be, in many cases, implemented a bit more easily, which is semi-device independent quantum information theory in some sense. We say, well, I may have black boxes. I don't know what they are doing. I may send quantum information from Alice to Bob, perhaps. So think of a scenario like BB84 quantum cryptography, where Alice really sends non-orthogonal quantum states to Bob. But to guarantee security, I need to make additional assumptions that I wouldn't have to do in the device-independent framework. And one assumption that's often made in this framework is that the states that you send in the scenario, they live on a Hilbert space of some bounded dimension. For example, they must be a qubit, basically. Yeah. Now, what this gives you, it kind of guarantees you that the states that you send are not orthogonal in some higher dimensional Hilbert space, so that an eavesdropper could spy on them in an unexpected way. So this is a very useful assumption, but the physical motivation is a bit hard. Like, how do you really want to make sure that there are no side channels and that this is what you can assume about your transmitted quantum states? Now, one goal of this work now is to say, perhaps in these protocols, we can replace these dimension bound by assumptions that are in some sense physically better motivated than the assumptions how these systems that we send respond to spatiotemporal symmetries. So think of something like spin less than or equal to 2 or something like this. Now, why is this physically well motivated? Well, in a special case, it is very well motivated. So if, for example, the group is the group of time translations, then this representation label is basically your energy, nothing but the energy. And so bounding the label would in this case amount to an energy bound. And this is in many cases arguably a very physically well motivated assumption to put an energy bound on your system. It's also in some sense closer to particle physics intuition, where you don't really want to count dimensions. Everything is anyway infinite dimensional, but perhaps you want to count particles in the sense that you count representation labels of the Poincare group or something like that. Now, we don't really know if this works, but in our paper, we have a very simple but useless protocol, which is nevertheless a kind of proof of principle that this can be made to work in some cases. So we look again at two polarizers and assume that for some reason we believe that the local systems respond with a representation label or spin that's upper bounded by some value J0 that we can say, whatever that is. It should be finite. And now here's a protocol, how Alice and Bob can certify Bell non-locality. So we assume that Alice and Bob share some random angle between 0 and 2 pi. Now what Alice does, Alice chooses freely between two settings now, theta plus and theta minus. These two angles are parameters of the protocol that are hopefully chosen in a suitable way. And Alice now inputs alpha plus lambda into her box. Bob doesn't choose freely, he's forced to input lambda into his box. And if they repeat this many times and they compute the correlation functions on the outcomes and they find that on theta plus you're very close to correlation, theta minus you're very close to anti-correlation, with a bound that scales like the third power of the belief you have on your spin, then you can certify non-locality. You can be sure that there's non-locality in your system without performing an actual Bell experiment. So this is something like a Bell witness that relies on the assumptions about how you think that your devices should respond to space-time symmetries. Now, the idea is, of course, that this is a very useless protocol. Doesn't really help with anything, but the idea is that a similar reasoning can be applied to actually make useful protocols. This is something we're looking at the moment. Good. Now, finally, final slide. The idea is that this can be, in one way or the other, interesting in experiments, for example, experimental tests of quantum theory. Here's, for example, an experiment that won our Ehrenfest Prize 2 years ago, the best paper in quantum foundations, where Bell correlations in a Bose-Einstein condensate were detected. Now, what's happening in such an experiment? Now, I'm not an experimentalist and I don't know the details, but what you see is that what's really happening here is you send a pulse of a certain duration and then you record an outcome. So typically, or in many cases, arguably, what you really know about your experiment is perhaps not your Hamiltonian or anything like that, because it's just a model that you put. But what you know for sure is that you've sent a pulse of a certain duration. At least that's what you believe. And that's where you do your statistics on. That's the parameter that you vary. So it's interesting to ask, what if we only make this assumption? What can we infer from this alone without making any other assumptions on our experiments, on our models? Or perhaps you only need to make a few other assumptions, like no signaling between certain parts of the experiments, or that may or may not include the validity of quantum theory. In this example, for example, it could help us to say what are the assumptions that go in the claim that there has really been Bell non-locality in the setup. Do I really need to trust all that the detectors are really measuring the POVMs that I believe that they do and so on, or perhaps fewer assumptions are sufficient? Or in general, you can ask under what conditions could such results falsify quantum theory in one context or the other. So there are a couple of proposed experiments that test quantum theory in contrast to more general probabilistic theories, for example, higher order interference. But typically these experiments do not really care so much about how your non-quantum phenomenon would really fit into space and time. And so the hope is also that this kind of formalism can say more about that. Okay, so let me conclude here now. So I've given you a framework of space-time boxes via group representation theory. Now this has led to some foundational insights, characterization of the quantum 2-to-2 correlations. To recap, the idea is also that this can perhaps lead to new protocols in quantum information processing. I've given you a kind of proof of principle in a Bell scenario. And hopefully, but this is really only speculation so far, this can also lead to some kind of novel experimental tests of quantum theory. This is really at least one of the reasons why I'm interested in this framework. Okay, so if you're interested, here's the paper. And with that, I would like to conclude. And thank you very much for your attention. Thanks.
Thank you very much for a very clear talk. Now the audience can ask questions. Yeah, I see some hands. Jaskaran, will you ask your question?
Yeah, thank you for a very interesting talk. So my question is, when you are verifying the Bell non-locality using your formalism, you use one-sided free choice.
Yeah.
Right? But you are also putting some assumptions on the system that your J should be less than equal to J naught. So does this fall under a device independent paradigm or semi-device independent?
That would be semi-device independent, I would argue. Yeah, I mean, it's not that these words would be perfectly well defined. Different people mean something different, but it's semi-device independent in the following sense. So if you do not put this additional belief on J, then you can actually always find a local hidden variable model. So it's really only that when you put this additional assumption on J, that you know that there must have been Bell correlations in your system, even though you didn't actually do a Bell experiment. Right.
Nice. This is very interesting. Thank you.
Thanks.
Manbendra?
Yes. Hi, Marcus. So that is a very interesting talk. Thank you very much. I have two questions actually. So essentially, if I just simply put that you try to formalize this entire Bell non-locality, but in a restriction of this like all your systems and the states are following this S or this G group, that means SU2 cross SO2 cross SO2. And also your measurement setups are also restricted to be symmetric in a sense, like you are dealing with symmetric states and symmetric operation. Is it, am I correct? So that means the entire thing, but you actually select out only, or you kind of restrict yourself to the states that respect this kind of symmetries, and also the operations, say measurements, also respect this kind of symmetries.
Kind of, yes. So so what I do not do, I think this is quite important to say, is I'm not saying that I only look at boxes that have a global translation, like rotation symmetry. Yeah, you could think of a maximally entangled state that has U tensor U bar symmetry or so. It's a very special state, and then you look only at those. That's not what I'm doing. So I'm not making any symmetry assumptions on the single boxes. All I'm saying is that I have boxes where these symmetry transformations can act on. So the probabilities change if I do these rotations. and they do in a consistent way. And I say that if I toss a coin and do a probabilistic mixture of these boxes, and then that the rotation also is basically a probabilistic mixture of the rotations. So this is why representation theory comes in and linearity comes in.
Okay.
Right.
Thank you. I got that.
This already implies something about the boxes, indeed.
Okay, thank you. My second question is, because I probably missed this part, because I was expecting that somewhere you actually introduce the time, in particular correlation in time, maybe through some causal structure and etc., but I don't see that. So can you please tell me that how this particularly, apart from the space part, time is coming into the picture?
Yes, so I think now you have two ways to talk about space and time in these scenarios. One way to talk about space and time would be the, in some sense, traditional way, where say space-like separated means it's a causal structure where there's no signaling from A to B. And time-like separated means like you have a causal structure that you perhaps write down with a directed acyclic graph, where an arrow goes from A to B, but not the other way around, right?
Correct.
There are these causal generalizations of Bell scenarios. This you can also do here. But in addition, you get something new where you talk about space and time in a new way, namely about the symmetries acting as transformations on single boxes. So you can pick out a single box like A and say now the input is an evolution time. So I know that I have a representation of the time translation group on the box, or the possible, in some sense, states that the box could be in. And it would also be interesting to study the interplay of both, for example.
Okay.
But here, time, it's more a representation theoretic notion of time that comes now in.
Okay.
Yeah.
Okay. Thank you very much.
Thanks.
I have a small naive question, Marcus. So it is sometimes said, or rather often, that Bell non-equalities, they are not a kind of based on quantum theory as such. So, I mean, it's not a result which is ingrained in quantum mechanics. Do you agree with that?
Yes, exactly. I agree with that.
Yeah.
So, I mean, even one of the first slides, whoops, no, I don't share my screen anymore, but when you recall the picture that I had, the classical correlations, the quantum ones, and the no signaling ones, then it's just a statistical property of a correlation to be outside of the classical set.
Right.
And to say what that means you don't have to refer to quantum mechanics. You just say, here's my probability table, and now I cannot write this in this classical form for this hidden variable lambda. So then it's non-classical. So this is indeed then not a property of quantum theory, but a general property that's sometimes phrased as a violation of local realism, which is more general principle.
Right. But when you impose a space-time structure on it, you have to presume that whether it is a classical space-time or in some sense, if it can also be quantized, that will also decide, I mean, what results you will get.
Well, not a priori. So the interesting thing in this framework is you don't have to decide in the beginning whether you have classical boxes or quantum boxes or more general ones, because you don't need to make any assumptions on what these boxes are to, for example, derive the theorem that I've shown you, that the tables must be given by representations of the group. Certainly, you know a lot more when you assume quantum theory. Then you know that the representation is given by a unitary representation acting on density matrices, for example. And then you pair this with a measurement operator with a Born rule. This gives you more structure. But a priori, the whole framework is agnostic to that. You don't have to assume quantum theory for that framework.
Okay, good. Yeah, so I don't see any other hands. So I think, we can thank you once again. I hope you also enjoyed giving this talk online.
Absolutely. Thank you.
Thank you very much. Yeah.
Thank you.
So our next speaker is Dr. Ashok Kumar.
Hi.
Hello.
Hi.
Can you share your screen just to prepare for your talk?
Okay, please give me permission to share this.
Yeah, I think somebody will do that shortly.
Okay, sure. No, still I cannot share it. I think the previous slide share has to be removed.
I'm getting this message in the chat that you can try once again.
Yeah, I'm doing.
Okay. Yeah, I also see the screen from the previous.
Yes, yes. Unless
presentation.
until that is removed, I think we can. Okay,
Now,
maybe.
now I
maybe.
can see you.
I think, yeah, now I can do it.
Right, I can
Okay.
see
Can
your
you see
slide.
my screen?
Yes,
Okay, great.
it's good. We just wait for a couple of minutes.
Sure.
Yeah. Okay, so we start with our second talk of this session. It's a pleasure to welcome Dr. Ashok Kumar. Ashok is currently an assistant professor in the Department of Physics at Indian Institute of Space, Science and Technology, Trivandrum. He has done his PhD in physics from PRL Ahmedabad in 2011. After a short postdoc term in PRL, he joined the University of Sao Paulo, Brazil, as a postdoc in early 2013, where he worked on coherent interaction of lasers with cold atomic ensembles. Subsequently, in 2015, he moved to the University of Oklahoma as a postdoctoral research associate, where he worked on generation of bright quantum entangled light with hot atoms and its use in quantum sensing and quantum imaging. So Dr. Ashok will today talk on quantum enhanced sensing. Over to you, Ashok.
Yeah, thank you. Thank you for introduction. So first of all, I would like to thank the organizers for giving me opportunity to talk about my recent work here. So what I'll be going to talk today is our recent work on the quantum enhanced sensing. In particular, I'll be talking about how we have used the quantum states of light to improve the sensitivity of the devices. So before going to actual talk or actual content of my talk, I would like to give a basic background actually. So the whole idea is we want to improve the sensitivity of devices. So that means first we need to know what are the factors that limits our sensitivity. So in all our classical measurement devices, the sensitivity is typically limited by technical noise or ultimately to the short noise limit. So we want to do something, some measurement beyond the short noise limit. Moreover, to understand how the sensitivity in the classical system is characterized, for that we need to understand what is the difference between classical and quantum noise. So being an experimentalist, if somebody asks you, so how would you able to, or how would you differentiate a classical and quantum noise? So to determine the noise in any system, for example, a laser system, what we do actually, we detect laser light by a detector, we amplify, and then we look at the noise as a function of frequency. And then we see a typical noise trace like this. So this is, before checking our system, we just check whether there's any classical noise or not. Or first, what we do, we turn off our laser and we see what is the trace we get, what is the noise trace we get at our spectrum analyzer. So this is the noise trace we get that we call electronic noise, or there could be some technical pickup noise that may be coming from some fan or AC or wherever. It can be some technical source of the noise. Moreover, when we turn on the laser, what we can get? We can get a flat noise background, white noise background. Of course, there could be some signal that we have already imparted to our laser. So we may get some signal that we have sent to the laser. And of course, on top of that, there will be a flat background. This flat background, except this technical noise, which is coming from some of the pickup noise or some technical noise. So we call that as a technical noise or the quantum noise, or that we call as a standard short noise limit or short noise of my light actually. So ultimately what the signal I detect, the ultimate height of that signal or ultimate resolution will limit what is my noise floor actually. So in the classical world, there are techniques to subtract out the classical technical noise. For example, you can use simple balance detection scheme and you can cancel out this common correlated classical technical noise. But there are no technical tricks that gives you that reduce or that avoids this technical noise, or that's a quantum noise. There is no technical trick that can get rid of you of this quantum noise actually. So now how to avoid or how to get rid of this quantum noise? The solution is you have to use squeezed light actually. So the squeeze light, to understand what is the squeeze light, we can, or everybody, or I hope everybody can understand that we can write an electric field in terms of two quadrature components. Actually, we can write electric field operator like simply like this. And if we expand this exponential, then we can get two orthogonally varying component. One is cosine component, while other is sine component. What comes with cosine or sine component, these component we call quadratures of the field actually. One, you can conventionally, you can assign amplitude, other you can assign the phase quadrature. The interesting thing is these quadratures satisfy the Heisenberg uncertainty principle like a position and momentum variable. And moreover, in the uncertainty relationship, you can see there is an equality sign. And if, these are the noise in the measurement of those quadrature X and Y. And if the measurement noise in these two quadratures X and Y is equal and equal to the minimum that is allowed by the uncertainty principle, that is 1, we call this kind of states as a coherent state actually. And if you look at the noise distribution of these noise distribution of coherent state in your phase space, it will look like a disk actually. So this is noise in X quadrature, this noise in Y quadrature. Now question comes, can we have the noise in or this limit, whatever the noise fundamental limit we get, we call that limit as a short noise limit, or moreover we also call as a, or in some part of literature you will find that this is also termed as standard quantum limit. So what we want to do, we want to have noise in our measurement or in our parameter beyond the standard quantum limit. So how do we do that? For that, what we can do, we can use squeeze state of light actually. So of course, from the uncertainty principle, you can have noise in either of the quadrature less than that is allowed by the short noise limit, of course, at the expense of increased noise in the other variable. If you can do like this, then of course you are squeezing your X quadrature. Your noise in the X measurement is, or X quadrature is less than that allowed by the standard quantum limit. Similarly, you can do noise in your Y measurement less than that in X actually. You can squeeze along Y direction. Or in principle, you can squeeze in any direction. This is called, we call this as a noise ellipse. You can rotate your noise ellipse any direction, whatever you wish, or wherever you wish. So you can get any, or squeezing in any combination of X and Y. So now with this background, what is our motivation in this project? Our motivation is to use these reduced noise properties of quantum states of light to enhance the sensitivity of devices. More fundamentally, what we would like to address, the question that, is it possible to interface quantum states of light with real life devices? For example, imaging system is well known to everyone. Other system that we explored is plasmonic sensors or plasmonic sensing platform. So plasmonic sensing platform is a very important medical diagnostic tool actually. These sensors, they detect, or they are widely used in chemical and biological sensing, or they are commercial sensors actually. So our goal in this project is, or I would say in this talk, the first goal I would like to address, how we have interfaced quantum states of light with those sensors, basically plasmonic sensors, and then how these sensors, or how we can improve the sensitivity of those sensors with the quantum states of light. In particular, what we are, or as a proof of principle, what we are doing, we are sensing a smaller change of air pressure or air refractive index by using those sensors. Moreover, at the end of my talk, I'll be talking about, is it possible to interface these quantum states of light with some of the imaging system, and we can get the quantum benefits in the imaging also. So that this will be my two goals. So as I said, the overall goal is to improve the sensitivity. But now we need to know, when we say sensitivity, how do we define sensitivity, or what we measure to define or to calibrate our sensitivity. So for example, suppose you have a sensor, and then you are probing this sensor with a light. So what this sensor can do, this sensor can change different properties of light. It can change the intensity of light, it can change the phase of light, it can change polarization, it can change different properties of light. So what a sensor does is sensor, suppose there is some change around a sensor. Let's say that parameter is P, that is of our interest. The parameter that is this sensor is sensing is P. So based on that sensing parameter, that parameter changes some properties of that sensor. Let's say that property is M. And that property M changes the property of the light. It could be your amplitude or it could be your phase. So based on all these like error, or we can use simply error propagation equation to get what is the minimum amount of the parameter that we can sense when we probe this sensor with the light. And that equation, you can simply, this is just a simply error propagation equation. Here one additional term we have introduced, that's like a square root of n, that tells you how many times you perform your measurement. Of course, if you repeat your measurement many times, then you can get a better sensitivity actually. So for a given sensor, these are just properties of the sensors. What we are interested here is just we want to impart the properties of light to our sensing device. So for these parameters we can consider as a constant. So for a given sensor, the minimum detectable change of the parameter that I'm interested will depend either noise, basically this is the noise term. This we call a noise, basically it's an intensity noise or phase noise or whatever the parameter you are measuring. So with this motivation, so what do we need actually? When we want to implement a quantum enhanced based sensor based on the light, then what do we need? We need basically three ingredients. One is we need a quantum source of light. We need a suitable sensing platform. We have to interface our quantum light with sensing device. And finally, we need to make an appropriate measurement. So with these things, we have to keep in mind, and then we have to when we interface all these three things in a one platform, we'll say that we can enhance the sensitivity or we can realize the quantum enhanced sensor. So with this, the outline will be like this. So first I'll be talking about quantum enhanced plasmonic sensing. That will be major part of my talk. And finally, I will highlight some of the recent work or some of the work we still keep doing that we want to improve imaging system by using this squeeze light. So with this, now I'm coming to my first topic, that is quantum enhanced plasmonic sensing. So these three ingredients I talked is first is a source of quantum light, that we use the source of squeeze light, that I'll talk in brief that what is that actually, what we actually use. And then of course we have used the plasmonic sensor, and then finally we have used appropriate detection scheme actually. That is the balanced detection scheme we have implemented. So now coming to the source of squeeze light. So how do we generate squeeze light? Though I have briefly explained what are the squeeze light in very beginning slide. Now I will tell you like a more formally, or how do we generate those squeeze light. To generate the squeeze light, you need to have a nonlinear medium, or you need to have something called squeezer actually. So what do? You start with a coherent state. I told you the coherent state is just a laser beam actually. Or of course, it shouldn't be that noisy actually. It's a quiet or noise laser that works at the short noise limit. This is a laser beam. You pump your laser beam to your squeezer. The squeezer is nothing but a nonlinear process that generates or that creates pair of photon into the field actually. It generates pair of photons into the field. And mathematically, it does this operation actually, as you can see. And at the output, you will get the squeeze light. And of course, mathematical form of the squeeze light or squeezing, or if you look at the squeeze quadrature, it will look like this. So S is your degree of squeezing. So if you squeeze one quadrature, of course, then you will anti-squeeze the other quadrature. And the amount of squeezing grows how much nonlinear is your nonlinear medium. So this is typical, like the idea we need. So if we look at now, I'm looking at more in the experimental prospects actually. If you want to look at the photon number distribution in those kind of light and want to compare with the coherent state, then in the coherent state, they satisfy the Poissonian distribution, or the photons that arrive to my detector, they are not temporally ordered. But if you have amplitude squeezed light, then your arrival of photon is temporally ordered actually. So they are temporally ordered. So moreover, here what we talked about something we call single mode squeeze state actually. So you are generating photons and you are creating both the photons in one mode of the field. But in principle, you can generate pair of photon and you can send these pair of photon into two beams actually. So in that case, you can generate twin beams. The nonlinear process or nonlinear medium that is generating pair of photons, you can emit those photons into two separate beams. So initially, these two photons were like in their vacuum state. And then of course, when you couple or after nonlinear process, what you do, you basically, when you generate photon in those fields, so what happens if you look at the individual field, it becomes noisier actually. But interesting thing is, these are the two modes, two photons you are generating in these modes. Interesting thing is, when you look at the joint quadratures, if you plot x1 versus x2, then you get a noise distribution like this. Similarly, if you get y1 and y2, if you plot y1 and y2, you get a noise distribution like this. So basically, you can get, this means you can get the amplitude difference squeezing, or you can get the phase sum squeezing. Now, again, the same thing, if you want to look at how the photons are distributed in two beams, then what would you say actually? Now, since my two beams are detected in two different detectors actually. So if I detect these two beams in two detectors, then you will see that, okay, of course, these are beams are generated in pairs. So once you get one, you will get another one. Similarly, you keep getting the replica of one to other actually. Now, what you measure at the output, you measure the intensity or intensity fluctuation, or that intensity fluctuation you measure in terms of the current fluctuation, because detector gives you current actually. If you look at the current output, it may look like this. It may look like noisy actually, because you don't have, you are generating pair of photon, but you are sending both the photons in two beams. But of course, this is the replica of this. But if you look at the noise here, then this noise will be completely correlated like this. So you have correlated noise or copies of correlated noise. Now, if you do difference measurement, you can get rid of, or basically you subtract it, you can get rid of correlated noise. So that means you can reduce your noise property. So that's the in principle, or that's how we get amplitude or intensity squeeze light actually. So how can we generate in experiments? So for generation of these kind of twin beams or two mode squeeze, there are different methods. So one is like a OPO, optical parametric oscillator, which is basically works on the principle of parametric down conversion. So you have a crystal, you pump your crystal with a strong laser beam or a laser beam, and it generates twin beams actually. And of course, if you put that inside a cavity, you can amplify the generation process. The other method that we use, or that we like more, is four-way mixing process. You know, the SPDC process is based on Chi2 nonlinearity. The process or the method we use to generate twin beams is a four-way mixing, and that is based on the Chi3 nonlinearity. What happens in this process, instead of in the previous process, there were 3 photons involved. Now here 4 photons are involved. Basically, 2 photons from the pump beams are absorbed, and due to energy conservation, 2 new photons, we call them as a signal probe and conjugate, they are generated actually. And these 2 photons are, of course, they carry quantum calculation properties. Moreover, in lab, what we have used our nonlinear medium, as a nonlinear medium, we have used rubidium vapor cell actually. We make laser combination, or we interface laser with rubidium hot atoms in a something called double lambda configuration. In that double lambda configuration, what happens? 2 photons from your lasers, your pump beams, are absorbed like this. They're shown by this purple line. And due to, again, energy conservation, 2 photons, we call them as a probe and conjugate, they are emitted. And they are emitted simultaneously. That's why they carry quantum correlation properties. Moreover, you can start with some seed process. You can start with some seed beam. You can seed your four-way mixing, and then by seeding, it can generate bright quantum correlated beam. They are as bright as you can see by your naked eyes, actually. And of course, where they will be emitted, where these 2 photons will be emitted, that is governed by your momentum conservation or phase matching condition. So, and these are the typical experimental parameter that we use in our experiment. And to check the squeezing, where whether we are getting the squeezing with those or not, again, you put your detectors and you detect your output noise, basically difference noise in a spectrum analyzer. And for these twin beams, we got a noise trace like this shown. This is noise, basically difference noise as the function of frequency. You have seen this is the noise trace we got. Now to calibrate or to know for the same power, what was our short noise? So we repeated the same measurement with our coherent state actually. If we use two laser beams having the same power as a probe and conjugate, this was our normalized noise actually. This was our short noise or standard quantum limit, and this is the noise trace we got with the four-way mixing. Here you can see that we have reduced the noise a lot. It's like a 9 dB of the noise we have reduced. If you don't have like a much sense about the logarithmic unit, 9 dB means we have reduced about 87% of the noise. We are left with only 13% of the noise standard quantum limit actually. So now with that, okay, of course, now what we want to use, we want to probe our sensor with this noise, less noisy beam, and then see whether we can enhance the sensitivity or not. That's the whole point. So now coming to the sensor that we have used a plasmonic sensors, and plasmonic sensors are nothing but they work on the principle of plasmons actually. The plasmonic sensor that we have used in our experiment were like an array of triangular nanohole actually. So what basically they are, we had a glass substrate. On top of glass substrate, we have a 100 nanometer film. And on that film, we had made some triangular nanohole structure as you can see here actually. Since their typical dimensions are less than the wavelength actually, they are sub-wavelength structures. So we don't expect much light transmission through those structures because of the diffraction. But the interesting thing is when we excite those structures, these are like the metallic structure. When we excite these structure with electromagnetic radiation, then there is a collective electronic excitation or there is a plasmonic excitation. Basically, our photons are converted to the plasmons, and then plasmon can propagate through those holes, and then they give us photons at the back surface. So in that way, we can have extraordinary optical transmission through those structures. Moreover, typical the EOT curve or extraordinary optical transmission curve that we got through those sensors was like this actually. So this is like if we send a white light or this broadband light, then we can get this kind of transmission spectrum through those sensors. Though we are probing those sensors with a fixed laser beam or fixed laser frequency. So for our working frequency of around 795 nanometer, the transmission of those sensors was 66%. Now, how these structure, they are just this nanostructure, how do they work as a sensor actually? So as we have seen, or I just told you, we pass light, we get a typical resonance curve through those structures. Moreover, if I probe those sensors with a laser beam of a given frequency, I'll have a given transmission T. Now, this is, I have actually. Now, interesting thing happens. Suppose some substance comes around those sensors like this. Then what it does, it changes the dielectric properties around those sensors. And that leads to a shift in the resonance spectrum. Earlier, my resonance spectrum was here, actually. It was in gray line, but it has moved, actually. So that means I was probing this sensor by just fixed laser beam. That means my transmission has been changed. Thus, by monitoring the change of the transmission of my laser, I can predict I can infer the presence of some substance around my sensor. Moreover, the problem is when the change in the transmission, this change is small. And moreover, when this change is the change of my transmission noise itself, in that case, I won't be able to resolve those. At the same time, if I probe these sensors with the squeeze light or reduced noise properties of light beam, I can detect the smaller and smaller changes. That's the whole idea behind quantum plasmonic sensing. So with this, so how do we interface, or how did we interface our quantum light with the plasmonic sensor? So the typical experimental setup that we use in our lab is shown here. So this is the four-way mixing setup. So what we did, one of the twin beams, we call that a probe beam, we sent through the plasmonic sensor, and other beam is directly sent to a detector, actually. We say this is a reference beam, actually. Now we place this plasmonic sensor in a hermetically sealed chamber, actually. What the idea is, around the plasmonic sensor, we want to make a control environment, actually. And then in that control environment, we want to detect what the smallest value of the change of the air pressure it can detect, actually. And then those change of the air pressure, how we are making air pressure change or air refractive index change, for that we are using ultrasonic transducer, actually, which is basically generating ultrasound waves at 199 kilohertz. Ultrasounds are nothing but pressure waves. They change the refractive index of your medium. And then the modulation, how strong your ultrasounds, that you can control by applying voltages through this one, actually. So you can modulate your change of the refractive index smaller or smaller or larger based on your driving voltage. Of course, in a separate Mach-Zehnder interferometer, we have calibrated at what voltage, what is the change of the refractive index that we get in around our plasmonic sensor. So this is a scheme for, and for the measurement system, we have used like a typical balance detection scheme. We use like a difference measurement, and then we look at our noise as a function of change of the refractive index at the spectrum analyzer. Again, to know that okay, we are getting any enhancement with the quantum light, we have to compare our result with the coherent state or with the laser beam. So we repeat the same measurement with the laser beam or with the normal coherent states, and then we do the measurement. As a result, when we change, or for a change of refractive index around those sensors, let's say 1.6 part into 10 power 7, we are making really small changes in the refractive index. We get a typical signal with a coherent state like this at 199 kilohertz, because we are modulating refractive index at that frequency, and corresponding to that modulation, we are getting a signal here. At the same time, everything we are keeping the same configuration. At the same configuration, if we repeated the measurement with the twin beams, our squeeze light, our signal height was the same, but the noise floor was reduced. So that means, obviously, we got the enhanced signal to noise ratio with the quantum light. Moreover, one can see that though initially we had 9 dB of the squeezing, we are left with 4 dB of the squeezing, because squeezing is sensitive to the losses, and we had losses to the plasmonic sensor like 34% and other optical losses. Moreover, to know at what point with the coherent state we won't able to resolve our signal with noise. This was signal, but noise was also of the same height, actually, for this much change of the refractive index. But at the same time, if we repeated at the same condition, if we repeated the measurement with squeeze light, we could still detect our signal clearly, actually, that means we have realized the quantum enhanced sensors. So moreover, to get what what is the best value, or what is the best value that we can estimate with coherent state. And with the twin beams, what we did, we plotted the signal to noise ratio as a function of the change of refractive index around those sensors. And what we have seen that with the coherent state, we can detect the minimum change that we can detect with 99% confidence level was 8.6 part in 10 power 9 actually, which is equivalent to the classical state of art sensing limit for those sensors. Moreover, we repeated the same analysis for the twin beams, and the smallest signal that we could detect was 5.5 in 10 power 9 actually. So thus we can detect the smaller changes with the quantum light. Thus we have obtained quantum enhancement by a factor of 1.56. Moreover, we calculated what is the quantum enhancement we are expecting with 4 dB of squeezing, that we got like a 1.58. So our results were pretty close to the theoretical limit. So thus, in this particular part, we have realized quantum enhanced plasma sensors. Of course, this work was highlighted in many places, and then it was considered like the Optics 2018 by Optics and Photonics News. It was news in Science and other platforms also. More importantly, what was like for the students, it was like a tutorial article on Optics and Photonics News, where they made a nice article on this, how you can use the quantum squeeze light for better sensors. So students, if they want, they can go over this tutorial article in Optics and Photonics News last year in September. So with this, just in the last few minutes, I will just highlight that we are also exploring the squeezing for enhancing the imaging system. So some of the articles are given here, actually the references. So the whole idea is that typical idea is the same actually. Here we were in the previous setup, what we were detecting, we were detecting our twin beams with a photo detector. Basically, we were measuring the intensity fluctuations, or basically temporal intensity fluctuation. But here what we are interested in the spatial measurement actually. This is typical our four-way mixing setup. Now we are detecting these two beams with the EMCCD cameras. If you detect these beams with the EMCCD cameras, then typical beams, actually these beams are bright beams actually. You can have the beam look like this actually. They look like this, and our goal is whether we can get the noise reduction in a spatial domain or not actually. You know, we get image here, where we can by doing a difference measurement, can we get the noise, or can we get rid of correlated noise? For that, just what we did, we extracted noise in those beams just by doing a difference measurement here. And then what we did, first thing is we have to see whether the noises are correlated or not. For that, what we did some cross correlation measurement. For that, we select a small area in one beam and then looked at the cross correlation of that. Basically, we select one beam, this small area, that is basically intensity fluctuation in that image, and this is the intensity fluctuation over the other image. We did a cross correlation measurement. Basically, we did intensity cross correlation or noise correlation, and as a result, we got this correlation curve or this correlation peak. That tells me that there are spatial correlation also. Moreover, just to check our setup, we just did the measurement for the coherent state also. As expected, we don't expect any correlation in two coherent states actually, or the images captured by two different coherent states actually. Moreover, if noises are correlated, then we should be able to subtract out the noise actually. We did the variance measurement in the intensity difference, or noise measurement in the difference of these two noises. As a result, we got a noise less than that is allowed by the standard quantum. That means we can obtain, or we can have noise below than this standard quantum limit. That means we can improve the imaging system by those kind of beams actually. Moreover, the next step is to realize, like to interface this kind of system with the real imaging system, as done in recent article where they have done with the BBO crystal or like in the parametric down conversion. But what the good thing about our setup is we have bright spatially entangled beam actually. So that means we are not limited by the photons actually. We have so bright beams, so we can have in principle single shot imaging actually. So in some of our analysis, we have shown that even in a single image, we can show the noise enhancement. Of course, in those kind of measurement, when people did with the parametric down conversion, they have to average out thousands of the images. But with our system, we hope that we would able to see that with like a single shot measurement. Of course, this is the result from this paper where they have really shown the advantage of the quantum enhancement. This was classical measurement. This was the quantum enhanced image. So with this, I would like to give a conclusion or summary what we discussed. So I hope I was able to convince that you can use the reduced noise property of light to enhance the devices. Moreover, I discussed about how do we generate squeeze light with the Fourier mixing process and how we have interfaced this with the plasmonic sensor and then showed that we can enhance those sensors. Moreover, I have shown that this kind of system can give you a spatial quantum noise reduction that we are expecting to have a significant enhancement in the imaging system. With this, I would like to acknowledge this work was done at the University of Oklahoma, US. So thanks Alberto Marino, who was PI of that group, and Jawad was a PhD student who was working with me on this quantum plasmonic sensing project. And these are our collaborators from Oak Ridge National Lab, and they were basically helping us to fabricate the plasmonic sensors because we are not expert in the plasmonic sensors. With this, I would like to thank you. And if there are any questions, I would be happy to take.
Yeah, thank you, Ashok. Yeah, now participants may ask their questions. Yeah, I'm sure Ashok must instruct for students also or amongst the audience.
Yeah.
Yeah, so if you don't have questions, let us thank Ashok once again. Thanks for joining us.
Thank you very much.
Our next speaker is Dr. Rajesh Nair. Hello, Rajesh.
Hi, hello.
Hello. Can we try sharing your screen?
Yeah. Is it visible now?
Hello.
Hello.
Yeah, the audio is a bit low. I can see your screen.
Hello.
Yeah, your audio is a bit low. Can you increase your volume?
Okay, wait a second. Yeah,
I can see your screen well.
Yeah, how is it now? It's clear, my audio?
It is still low. It needs to be ramped up a bit.
Can do. Is it fine now?
Yeah, it's better. Yes.
Okay.
Yeah, I think it's okay now. So we will start in 5 minutes.
Okay.
Yeah. Okay, welcome to the final talk in this session. It's a pleasure to introduce Dr. Rajesh V. Nair, who is a faculty member at the Indian Institute of Technology, Ropar. Dr. Nair, he did his PhD from IIT Bombay in 2008. He was postdoc at 20 Netherlands in 2010. Also has been K.S. Krishnan Fellow in 2012. He's a INSA Young Scientist Prize winner in physics of 2015, also a senior member of Optical Society and a fellow of Swarn Jayanti Fellowship DST 2019-20. He has been a faculty member at IIT Ropar since 2019. So today he'll be talking on controlling the spontaneous emission of nitrogen vacancy centers using photonic structures. Over to you, Rajesh.
Okay, ma'am. Thank you for the introductions, and I also thank you, the organizers, for this nice invitation. So today I will share with you some of our understanding of some of things which we learned about controlling the spontaneous emission of color centers or the nitrogen vacant centers using photonic structures. So here you see a nice picture of a peacock feather. Everybody must have seen this at one point of your life. And so these colors actually come because of these nice photonic structures inscribed on this peacock feather. And this is, if you take one feather, one barbel out of it and image it in your lab, this is the measurement done at our lab, you can see that this shows a particular peak in reflection. So that's why you see different colors, depends upon which kind of bubbles and which kind of structure you image. And this is one of the nice photonic structure that is available in natures. So people try to mimic these kind of structures in laboratory and do more interesting fundamental physics and also interesting application using that. And I'll show you in my talk using one of these kind of structures, what we do with controlling the spontaneous emission. Okay, so I'll give a quite brief idea about the NV centers. What is this? What is its properties? Or what are the challenges? And then our experimental results or our understanding of how we can control the spontaneous emission in both intensity and rate, and how we can use this engineered photonic structure to modify the properties of these NV center emission properties. And I'll summarize my talk and will tell you our future endeavors or future directions, which is more into the quantum regime. Okay, so before I get into my talk, our group at IIT Roper, it's now nearly 6 years here at Roper. So primarily we work in an area called photonic crystals, which is similar to an electronic band gap material, where you can control the photon density of states, and in a way you can control the spontaneous emission. So we have been working on this field for quite a long time, and a couple of papers in this last 2 years is listed here. And we are also interested in with the disordered photonic structures, where when I say disorder means the disorder in the dielectric constant, the randomness in dielectric constants, and which we are also interested in that. And it has applications in anti-reflections and antibacterial. So we have a few papers recently published in that area. And off late around 2016-17, we started our interest in color centers in diamond, or the nitrogen vacancy in these diamonds, which has a lot of interest towards in the especially in the quantum technologies or quantum photonics. So I'll tell you some of our understanding on that, how we can we control its properties. So there are many other areas also we work in our lab. Okay. So before getting into the color centers in our NV centers in diamonds, what just takes a minute for what are solid state emitters. And so solid state emitters are basically basically the defects in many materials, the vacancies in many materials, like the diamond or the silicon carbide or the 2D material like hexagonal boron nitrate. And why this is so interesting for optics or photonics community, it has a very narrow electronic transitions. And these systems are proposed as a source of single photon, and it has been demonstrated also. And these some of these defect state have a long spin coherence time, and one can manipulate or excite, manipulate, read out the spin state using completely optically. And these properties are tunable. And the most important is that all these solid state emitters can be integrated into photonic structures like photonic crystals or cavities or waveguides. So it has a technological perspective also. And the people looked at the atomic defense or the solid state defects in many materials like diamond, silicon carbide, for looking at these kind of properties. And one of the prominent or the most explored or most exciting defects or solid state defects is that defect centers in diamond. And because diamond, as you know, is a large band gap materials, which is optically transparent, but these defect states actually give the colors to these kind of diamonds, as like, for example, depending on what kind of impurity it has. And there are many defect states in diamond. When I said defect state is a vacancy of an atom, and adjacent to that, there is a foreign substitutional atom. For example, if my substitution atom is a nitrogen, or I can have a chromium, or I can have a silicon. So depending upon that, I have a different defect states. So one of the nitrogen vacancy which actually appear in two states, so two charge states. One is called the NV0 states. Basically, this is a diamond unit cell, and we have a vacancy of carbon atom here, and adjacent to a nitrogen atom. And if this system has a 5 electrons, 3 from the dangling and 2 from the lone pair, so this is called a NV0 center, and this is a spin-half system, and that this has a 2 energy levels with the ground state and excited state, and this is not that something quite interesting. And what is more interesting for in the diamond color centers is the nitrogen vacancy negative center. Basically, it's again a same kind of defect state. You have a vacancy of carbon atom, and adjacent to it there is a substitutional nitrogen atom, and this pair is actually called as an NV center when the system has 6 electrons, and 1 extra electron is captured by donated by some donor in the system. And this defect state, because of these defects, you have energy level, the energy states within the band gap. So you have a ground state, which is a triplet ground state and triplet excited states. And this triplet ground state is again 0 and plus or minus 1, and the excited is 0 and plus minus 1. And there is, once you shine with the green laser, 530 nanometer laser, I can take the population from the ground state to the excited states. And this can de-excite by 2 ways. Either this direct transition from these are spin conserving transitions, or it can also take a intersystem crossing, which is called long path. And this is the NV minus center. And in my talk, when I say NV center, what I mean is NV minus. So if you look at the energy level diagram of NV center, as I said, it is ground state, the electronic ground state, which there is a vibrational levels, and there is an excited state, and there is a vibration level. And if you give some energy, for example, Fi32 laser, if you bring the population to the excited states, and it can come down through 2 main transition. One is called a zero phonon line transition, which does not involve any phonons. Okay, and so these are called zero phonon lines. It comes from the 0 state in the excited state to the 0 state in the ground state. And there can be phonon induced transitions also, as I shown here. And when you measure the NV center emission spectra, you get a very broad emission spectra. And this line, this particular small kink you see here, around 640 nanometer, which is a zero phonon line. And you have a very long, the phonon sideband emissions, and which is one of the negative part of NV center, because it has too much phonon induced emission. So other interesting aspects of NV center is that it is, as I said, it can be optically manipulated, the spin states. So what we call is the optically induced spin polarizations. You start with the population in the ground state, you excite it to the excited states. And in the second step, it can come down to the ground state, have a direct transition, but some of the population can also go to these metastable states. And in the step 3, this metastable state has a high probability to come to the ground state. And in the finally, you have more population in the MS equal to 0 state to the ground state. You start with a kind of equal population here, but you end up after one optical cycle, a more population in the ground state of this NV minus center. And this is what's called the optical induced spin polarizations, where people try to manipulate and read out using optical methods. And once I have as you see the energy level also I can excite then, and I can get the population in the ground state, and I can parallelly apply a microwave field. And the frequency difference between these 0 and minus plus minus 1 state is around 2.87 gigahertz. And if I apply simultaneously a microwave source, I can drive the population from the MS equal to 0 state to the MS equal to plus minus 1 states. And if I simultaneously look at the fluorescence intensity, I see a dip because the population transfers from MS equal to 0 to plus or minus. And this is why people in the community call these are dark states. And these states I can also control using magnetic field like a Zeeman splitting. And this is the basis of magnetometry that I can, by looking at the difference between these two dips, I can identify what is the application of magnetometry in this application. Applications in NV center sense, because it has applications in biology compared to others, quantum dots or dyes. These are not photo bleaching or photo blinking, and it has application condensed matter physics where people interested in magnetic the imaging and all these materials. And this is a typical the sensing application. It has electric field temperature, and in quantum optics or in it has shown as a system that can emit the single photons even at room temperature. So that is what is more exciting for quantum people working in quantum technologies and all. Okay, so having said all nice things about NV minus or the nitrogen vacancy center, this is the field is not that good if you really look at the system, because there are so many challenges has to be overcome if it is to be used for any practical application. And as is shown earlier, that the spontaneous emission spectra of a nitrogen vacancy center look like this. Okay, it has a very broad emission, and there is a peak which I shown with an arrow here, which is a zero phonon line. And the community want higher spectra, something I shown in this inset. Okay, so this is, if the spectra look like this, it could have much interesting, because you don't have any phonon induced decoherence in the system. You have pure electronic transitions. And the other problem which happens in the case of nitrogen vacancies, that when you pump the system, the NV minus converted to NV zero. Okay, what is called the recombination ionization process, or we call it charge state conversion process in NV center. So that is another disadvantage of this, because we don't want NV minus to go back to NV zero. What we want is always NV minus. And the other issue is that the emission intensity, or the emission which is funneled to this zero phonon line, which is at 640 nanometer, is extremely low, is 3%. Even if I cool the system to ultra low temperatures, it is still emission is very low into that man. So there are ways to, so people looked at what are the ways at which I can avoid this disadvantage of NV minus or the NV center, and can be use it for study more nice physics, and also the application perspective of it. And that is where the photonics community, the photonics community has a role to play. Okay, that's where we get into the field. Okay, and there are few works. I'm sorry if I missed something. This is something which I was quite interested. And there was work based people use plasmonic system, like the previous speaker was talking about plasmons. So these are some work recently published in Nano Letters, where you have an NV center, as you see as a nitrogen vacancy center, and you have a plasmonic field to control the spontaneous emissions for the NV center emission spectrum. One of the things which is quite mistakenly see in literature, people talk about enhancement or controlling the emission using emission intensity, which is something is not a right parameter to talk about. For example, here you see a 90-fold enhancement in emission intensity, but absolutely there will be no rate change. So it is all about important to have, when you talk about the effect of photonic structure on a quantum emitter, whether it be center or single quantum dots or whatever it is important to talk about the emission rate, for example. I'll show you in the next few slides, we get a huge changes in intensity, but we don't get that kind of change in the emission rate. Okay, until unless you cannot control the emission rate, it's just a filtering effect. So there are many other platforms also used, and we use another platform which is called photonic crystals or the photonic band gap systems, because we had a lot of experience on that, and we thought of using photonic crystals to control the emission properties of these NV centers. Okay, so those who may not be aware of photonic crystals, so photonic crystals are basically a periodic dielectric system, just like an atoms arranged in a periodic manner in a semiconductor. Here the refractive index is arranged periodically. So these are artificially made systems, and due to this periodicity, when the light propagate through this system, the right conditions, basically the Bragg condition, a certain frequency is reflected back. Okay, and if you solve the Maxwell's equation for a homogeneous medium, and you plot frequency versus wave vector, you get a green dotted line, which is what we call as free photon relation, or the free space dispersion relation. And if you do the solve the Maxwell's equations in a photonic crystal medium like this, and you get a band gap or a stop gap, that means a certain in the frequency with this yellow band is not allowed to propagate to the system. Change in density of states. So you look at density of state as a function of frequency. Wherever I'm getting a band gap, I'm get zero density of states. And from time dependent perturbation theory in quantum mechanics, so if you have a density of states, which is rho here as a function of frequency and position, if you have a system which can control the rho, you can control the rate. So I have a system now embedded artificially. I can change the density of available state for the emission, and in a way I can control the decay rate, and hence I can control the lifetime, because lifetime is inversely proportional to the decay rate. And these are the typical measurement what we do in the lab. This is our result. So you look at the decay rate, or you have a kind of a rhodamin dye or so, and you look at the rhodamin dye emission decay, these black symbols you see here. And if I put the same emitter in a photonic bandgap medium, and I look how the decay happens, you can see the decay is getting very much slowed down. The decay becomes lower, and it is because the decay is not allowed by the bandgap, but still it is allowed in real systems, because effect scattering and all happens, but can be controlled using photonic crystal. So the question that we ask, if we can do this, why not controlling the NV center emissions and see whether we can use this system to control the NV center properties. Okay, so that's what we started in 2016. We made photonic crystals. A clear inferences here that we are not working on single NV center. Okay, we are working on an ensemble of NV centers, and our work towards single NV center is just progressing. And probably next conference I'll be able to give you the data on that. So we have nano diamonds with NV center, which is decorated over these photonic crystals. So first we measure the reflectivity of the photonic crystal as a function of wavelength, and you can see that there is very peak is coming for the photonic crystals, and the red and blue correspond to different photonic crystals, means different lattice constant of the crystal, and that corresponds to different band gap of the crystals. And the black one is far to the blue side, and that we use as a reference. And this is another important thing one need to keep in mind whenever you look at a photonics paper. When people talk about changes in emission, what is the reference you are using? And this reference is always a game changer. Depending upon whatever reference I use, I can say I have 10 times enhancement, I can 20 times enhancements, something like that. Okay, so this, and you look at the wavelength range where we are getting the photonic band gap of our system, and that is quite interesting. Keep this wavelength in mind, because that's what we are going to next. And once we have understand, okay, our photonic crystal has a band gap, we want to see whether it can be controlled using, it can be used to control NV center emission. So for that, we need to do emission measurement. So we built up an experiment in our lab using a confocal geometry. And this is a setup. We excite the NV sample with a 532 laser, and we collect the emission in the confocal geometry. And this is a typical sample image you see here. One, you can see that this is the sample actually, and then we send a reference measurement. What you see here is a broad emission with a very narrow peak at the 0 phonon line. Okay, now let's measure these emission spectra when these NV centers are combined with photonic band gap. So that's what we want to do now. So now I have a photonic crystal here, and on top of that, I have a NV center. And so I'm exciting from the backside geometry, which is we call the rear side geometry. I'm looking at the emission measured from the in the rear side geometry. So look at this is the intensity measurement as a function of wavelength, and the black curve is a measurement for the reference sample, which just look like a typical NV center. And when I measure for photonic crystals for 287, which is a lattice constant, you can see that there is a dip there is a drop in emission intensity. And if I measure for another sample, you can see that there's a dip now shifted to close to 700 nanometers. And that change in dip is actually because the band gap is different for these two samples. So correspondingly, we expect the emission intensity drop should also change with wavelength. And this spectrum may not be that interesting to grasp. So in our community, what we always represent intensity ratio. And the intensity ratio means the intensity of the sample divided by the intensity of the reference. And if there is no change induced by my sample, I should get intensity ratio unity. But you'll see in the curve, when I divide this blue by black or the red by black, what I see is that there is a very appreciable dip in my emission intensity. And this actually shows that the emission intensity is drastically reduced by photonic band gap. Now you can see that we are very happy. We got one of the best suppression in emission intensity by photonic crystals. But when I talk the rate, you don't see that kind of changes. And what is more interesting here, so if you look at the blue spectra here, for example, the blue, you can see the band edge, basically the photonic band edge is actually coinciding with the zero phonon line, which is around 640 nanometer. And the band edge has a property that the density of state can be increased at the band edges. So we look at that, and if you look at the that's zoom the spectra, you can see that and the zero phono line is much you don't get this kind of hello.
We are losing your audio in between. Maybe you can try to switch off your video. Let's hope it will improve the audio. You can switch off your video.
Okay.
Yeah.
Okay.
Yeah. Please go ahead.
Okay. So at this, how these bandits can be also used to enhance the NV center emission, zero phono line. That's why we intentionally use that particular photonic crystal there. And you can see that we got a better visualization of the zero phono line of NV centers. And these results are quite repeatable across the sample. You can see that there are a few millimeters, we can repeat it. And so it was a very nice work we did on controlling the NV center using photonic crystals. And we also look at the saturation behavior zero phonon line. You can see that our photonic crystal, where this is at 632 at the zero phonon line, our photonic band edge is actually giving a better saturation or better photons as a function of pump power. And we also look at the ratio of NV minus to NV zero. And as I said, we want NV minus. We don't want this should happen, but when we have combined photonic crystal, it is showing a better control on negative charge states. And this work we published in Optic Letters a couple of years back, and this was editor selection also in the Optic Letters. So this is what more interest for physics or the people who are interested in controlling the emission. But there is altogether a different community who are interested in using NV center for biological application, like biomarkers and all those things. And they don't want to suppress emission because they want to have more and more photons to come. Okay, so we look at the geometry quite different from the previous one. Instead of looking from the back side of the sample or the rear side, let's look from the front side of the photonic crystals, where you see the nanodimensional, then you have the photonic crystal. And when we did this measurement, we could actually measure the enhanced emission intensity from the photonic crystals. You can see that because of the photonic crystal, we get this kind of huge intensity enhancement. And this is quite useful for people working in biology. And so actually we can use photonic structures either to suppress or to enhance. So one of the cover article came in Physics World about our work, that the title of the journal is choose the nano diamond shine brighter. So we can make a system which is already bright and we can make it more brighter. So as I said in the introduction also, the line is to tell you really there is a change in density of states, because in the Fermi-Gordon rule intensity is not, it's a density of state related to the decay rate. So we wanted to now look at how this result, how the rate of spontaneous emission depends on photonic band gap structure. So we made a structure, an experimental setup to measure it. So we have a picosecond laser, and which is focused on our sample using a microscope objective. We collect this light and send to a camera to see where actually we measure, because these are microstructures. We need to exactly we are probing on the sample down, and we pass it through a long pass filter and get the emission spectra to see where we are measuring what we see in intensity spectra. And once we are happy with that, we put this flip mirror up, and it will take to a single photon detector for the decay rate measurements, which is connected to a driver and a time correlated single photon counting unit. So we did that measurement, and this is a typical decay curve we measure for an NV center. This intensity as a function of time. In the previous slides, we were talking about intensity as a function of wavelength. So that's the difference. And another problem or another issue with the decay curve is how do you fit and take the lifetime out of it? And there are many ways. Many people, there are people use stretched exponential. There are people who use log normal distributions. But for us, it was nicely fitted with the bi-exponential fit, which is also used in a PRL paper where people try to understand the quantum dot emission using photonic bandgap structures. And you can see the residuals also very low. And so we are happy with these fits. And in the further talk, I'll be talking about an average lifetime, which is the result of two exponential fit to the measured decay curve. And this is the, so when I do the decay rate measurement without any wavelength filter, we don't see any changes. But if I actually do a measurement of different wavelength filters in our NV center emission spectra, you can see that this is a spectra which is measured, and you can see different colors we see. And if I measure at each of these wavelength, I can see that the decay rate actually decreases as a function of wavelength, and which is a quite well-known thing in the community. And this NV center, NV0, actually this is NV0, phonon sideband, which is a higher lifetime. And as I go towards the NV minus regime, the lifetime get decreased. And this is also confirmed that our measurements are correct and the values are okay with the reported values at many publications. So let's now look at the same experiment in terms of decay rate. Okay, so I'm, instead of intensity measurement, I'm measuring the decay rate. So I'm exciting again the same geometry, which is a rear side geometry. I'm sure you understood now what is the geometry now. And then I measure the decay rate, and I can see that you don't see much change actually. The black one is a reference sample, and the blue one is the sample where I expect a effect of density of state. And once you fit it, once you fit this measured curve with our double exponential, we got an average lifetime for the sample, which is our PS287, is an 18.8 nanosecond, whereas for the reference, it is 16.2 nanoseconds. So there is a around close to 3 nanosecond increase in lifetime we got slower. Okay, the emission is quite slow down, and that is because of the photonic bandgap effect. And we actually got a 16% increase in the lifetime. When I say 16%, one should it's a quite big number, because the sample we are using, which is a photonic crystal, has a very low refractive index. These are not silicon based system where you can get a huge 80 to 90% enhancement changes in lifetime. But these are very simple sample, because that's only we can make it a ROPR. And we also measure the lifetime at different regions of the sample. And I plot a kind of a distribution in this. So you can see here, the distribution from the sample is quite distinct from the reference. And there's no overlap we have seen. So this clearly shows that the NV center, not only the intensity, but the rate is also getting affected by our photonic structures. And we did this the decay rate mapping at different wavelengths. At the previous one was at 660 nanometer, which corresponds to the photonic bandgap, which corresponds to phonon side band of NV minus, and 638 is a zero phonon line. And we got slightly higher decay rate here, the lifetime here, but there is a bit of overlap with the reference. And the 700, the sample become a lower lifetime, and the reference become higher lifetime as we expected, because there is no density of state effect at 700 nanometer, because it's quite far from the bandgap. And if you look at the, this is a right plot, if you look at the average lifetime as a function of different wavelengths, so you can see that as expected for our NV center, for photonic crystal also, the lifetime is getting reduced. And at the band gap, the lifetime for the sample is higher than the reference because of the band gap. And at other wavelength, it is quite different. And if I take the delta T, which is the blue minus black, and this is what you see here. And so whenever I have a band gap which is close to 660 nanometer, I have the high delta T values. And one can argue, in fact, the referee of when we submitted this to a journal, the referee was quite concerned about this kind of distribution, because the question is, these are very, very small space, even though within the error bar is within the data points. So we did, according to us, for the referee suggestion, we did a test called Kolmogorov-Smirnov test. Basically, if you have two distributions, and if you do this test, if the distributions are arising from the same, they will be get overlapped. If the distributions are different, they don't overlap. So you did the distribution, you can see that both are quite different. And that means both these distributions are actually arising from a different distribution set, because one is sample and one is the reference. So you can also see in this picture that the increase in lifetime is also compensated by a decrease in lifetime at other wavelength. And that actually follows from the Barnett's Loudon sum rule, which was published in quite long back in PRL. And again, like in intensity, I can look at the front side geometry. And as I expected that the lifetime, when I measure from the front side geometry, is quite low in comparison to the reference sample. That means the rate is getting, the lifetime is increased. That means the rate is now become faster. So because of these crystal, which is reflecting the light back, because the light cannot propagate, it actually made this like the lifetime is getting reduced, so emission become faster. So which is also we verified the whatever we see in intensity also with the rate measurements. And again, I can look at the similar to the rear side geometry, how the average lifetime move depends on as a function of wavelength. And as you see here at 660, which is the band gap of the photonic crystal, the lifetime is lower compared to the reference sample. And if I look at the delta T, which is the difference between the blue and black, and you see now the lifetime delta T is negative, because it is now the opposite to what I said in the previous slide, which is the front side geometry. And so I put it here again to just for your comparison. So in the rear side geometry, you have a band gap effect, and in the front side geometry, the sample, you have kind of the lifetime is quite reduced. That means rate become much faster. So this we just recently published in Journal of Optics. And how much time I left? Hello. Hello.
Yeah, you have a couple of minutes.
Okay. So another thing we also interested is looking at how how this decay rate actually depends on pump power when you do within this, when these NV centers are in this kind of photonic structures, and can we control one of the biggest issue of NV center in many applications is a charge state conversion, that conversion of NV minus to NV zero. So we did this experiment and we looked at at wavelength 600 nanometer, which is correspond to the phonon sideband of NV0. And you see as I increase in pump power, the lifetime is reduced as expected, and it is quite discussed in many publications earlier. But what was interesting in our work, when we did the same measurement at 700 nanometer, which is purely an NV minus, because 700 nanometer corresponds to the NV minus phonon sideband. So we see that instead of decreasing, the lifetime is increasing. And that is clearly showing that the lifetime of the excited MS equal to zero state is increasing. So I can, if I can build up the population on MS equal to zero state in the excited state, I can get transition that to the MS equal to zero ground state, because it's a spin selective transition. So in a way, I can achieve what is called as the increased spin polarization in this NV center. And if I do the same experiment at the band gap wavelength, which is 660 nanometer, the reference goes as expected, but because of the band gap, I can further increase this average lifetime. That means I'm even generating populations at the MS equal to zero state in the excited states. And if I again look at the difference between these two, you can see that the delta T is higher. That means I can build up the population in the MS equal to zero spin sub levels of the NV minus state. And in a way, we can say that the conversion of NV minus to NV zero is also affected by the photonic band gap at low power, and as you increase the pump power, there is no difference between the reference and so maybe I can discuss some detail if somebody is interested later. And this work we published recently in Physical Review A. And we can also look at the same process at 630 nanometer, which is a zero phonon line of your NV minus. And I can see that at zero phonon line, where the bandits coincide with my NV center emission, you can see that as expected, the lifetime is decreased compared to the reference sample. So this in a way related to the earlier intensity change, which I talked to you, that the bandits can also be used. And this result actually give a clear message that if you can trap NV center in a photonic cavity where density of state change can be much stronger than a bandage of the photonic crystal, these kind of process can be even ultimately controlled and with a very high control on these emission rates. And that's what something we are planning to do in our lab now. So in the till previous slide, I was talking to you ensemble of NV centers. As I told you in the initially that we are not working on single NV center because we wanted to learn this field. We wanted to understand how we can control this because we are very new to this quantum photonics or the NV single emitters. So we wanted to first understand the ensemble of NV centers. And then we are going to now move to single NV centers. With bit ambition, we brought these samples and we developed an experiment which is called the photon correlation measurement or the coincidence measurement. And basically looking at the intensity correlation, or theoretically you say G2 curve. So this is something we theoretically simulated using a mathematics available in this paper. So at the zero time delay, we expected zero G2, that means the coincidence zero. That means there is a pure single photon emission. So we brought this single NV center. At least the claim was that the diamond has single NV center. So we built up an experimental facility. It's very quite complicated. And we made a confocal scan of that sample. So this is a single NV center, what you see the bright spot here. And we could measure the decay curve. And we got the values that what reported in literature. But when we did the G2 curve or the intensity correlation, you can see that we don't get a zero there. Okay, we don't get a dip there. We still get a peak because as a laser, that's why we are getting this equally spaced lines. The coincidence is one always. And so we don't get. So we do not have a single NV center in this nano diamonds. So I think we need to improve our samples, and probably next time we'll able to have the single NV center. And once we are able to identify the single NV center or the single the photon emission, then we have a lot of things to do with those kind of samples. And so probably I conclude now. I hope I could give some idea about how we use our photonic structures to control the emissions. You can suppress or you can enhance it, and how the bandits can be used to enhance the emission rate and the intensity. And and in future, what we are trying to do in our lab now, we got a very good funding recently. And so we are going to build up experiments generating these single photons or single NV center in photonic cavity structures and at low temperature. Okay, so if you notice that in my work, all the work I was doing is at room temperature, but we are getting a cryostat and we are going to do this experiment at 3 to 4 Kelvin. And hopefully next time we'll have more result, which will be exciting to more quantum optics people. And with this, I thank my students. And the work I presented, actually the work by Sachin Sharma. He's submitting his thesis this week or probably next week. And he's going to postdoc with Merrill Carlos, one of the pioneer in the NV Center magnetometry. And we have been, I thank all my funding agencies who's very generous to fund my lab so that we could do all these nice experiments, and my collaborators and my master students. And I thank you also for your time.
Thank you, Rajesh, for this interesting talk on state-of-art experiments on nitrogen vacancy centers. I am afraid we are very short of time. I don't have time for questions, but if the participants have any questions, I think they can write to Rajesh and he'll be happy to answer your queries.
Yeah, sure.
Okay, so with that, I thank all the speakers in this session, and this session is over now. Thank you.
Hello, everyone. Welcome to the third session of the day. And then the first speaker of this session is Dr. Day5 Liu. Let me introduce him with a few words. So Dr. Day5 Liu is now an associate professor in the Shenzhen Institute of Quantum Science and Engineering and the Department of Physics at Southern University of Science and Technology, shortly called SUS Tech. He received his bachelor's degree in 2007 and PhD degree in 2012, both from the University of Science and Technology of China. From 2012 to 2017, he was a postdoctoral fellow in the Institute for Quantum Computing at University of Waterloo. In August 2017, he joined SUS Tech as an assistant professor and was promoted to associate professor in May 2019. His research interests lie in quantum computing, quantum simulation, quantum control, and quantum machine learning. He is an experimentalist in spin-based magnetic resonance systems, including the nuclear magnetic resonance and nitrogen vacancy centers in diamonds. So today he will be talking on experimental quantum principal component analysis via parameterized quantum circuits. So with this, I will request Dr. Day5 Liu to start the seminar. Thank you.
Okay. Thank you, everyone. Can you hear me clearly and can you see
Yes.
the slides? Okay, sure.
Yes, we do. Please go ahead.
Thank the organizer to give me this opportunity to present our work. Actually, it's my great honor to be here to share our research with you guys. And today I'm gonna talk about experimental quantum principal component analysis via parameterized quantum circuits. And my name is Day5 Liu. I'm from Southern University of Science and Technology. Actually, you can just pronounce this like SUSTech. It has no relation with a very famous University of Quantum Information Research, USTC. There's no relation between these two universities. And actually, this is our 10th anniversary of SUSTech in this December. Okay. Oh. In this talk, I'm gonna to split the talk into 3 parts. The first one, I will briefly introduce what is principal component analysis algorithm. We call it PCA from now on. And then I'm gonna talk about how to implement the quantum version of PCA using the parameterized quantum circuits. And the last one is our recent experiment, QPCA algorithm for the problem of face recognition. And unfortunately, this paper is just done. It's still under review, and we don't, due to some reason, we don't put this on archive. So I'm sorry that you cannot download the manuscript from archive yet, but hopefully it will be online soon. Okay, when machine learning meets quantum science, with the rapid growth of the power of the GPU in the recent years, we have witnessed a rapid development of machine learning from this famous AlphaGo robot, which can beat the world champion Li Saido in the classical game Go, and to this one, which is a self-driving car. And people now are getting used to the achievements of machine learning. Now, if you tell a person that, oh, we have made some machine learning breakthroughs, and the people will say, wow, that's just ordinary. But if you tell the people that we do something new in the field called quantum machine learning, which is the overlap field between quantum information processing and classical machine learning, and the people will get excited. Then the core question is, what is quantum machine learning? What is QML? Actually, you can divide the field of quantum machine learning into two. Here is a picture about the type of algorithm and type of data. If your type of data is classical and your type of algorithm, that is the tool to tackle the data, is classical, so it is called CC. If the data is classical and the algorithm is quantum, so we call it CQ. And if the data is quantum and the tool is classical, then it's QC. And the last one, that both the data and algorithm are quantum, so that is QQ. Then the first quantum machine learning is defined on QC. That is, the target problem is some quantum problem. And the tools that you used to work on this problem is a classical machine learning method. One of the pioneering researches on this QC is by Matthias Troyer to solve the quantum many-body problem, which is a famous problem in condensed matter physics, with the new developed artificial neural networks. And this work also triggers many subsequent researches on this QC field. And the other one, which is also called quantum machine learning, is the yellow one, where the problem is classical, but the tools that you use to tackle the data is quantum. And I think the most famous one is HHL algorithm to solve the linear systems of equations by Harold, Hasadin, and Seth Lloyd. Although it seems not directly related to machine learning, but this algorithm actually underpins many quantum machine learning algorithms. So I think this is the most famous one to date. And in this talk, we are gonna focus on the yellow one, the CQ one, that is the problem is classical, and the algorithm that we used to solve the problem is quantum. There is a very nice review paper in quantum machine learning in the year 2017 by Jacob Beaumont and Seth Lloyd. And in this paper, they summarize all the machine learning algorithms, quantum machine learning algorithms in a table. And in this table, you can see that there are not so many classical algorithms that have quantum speed up at present. And there are even less experiments in this field. One of the well-known one is to realize a quantum support vector machine in the system of nuclear magnetic resonance, the NMR. It's published in PIL in 2015, where the authors use the NMR quantum processor to run an algorithm of a quantum support vector machine, which can be used to distinguish the handwriting 6 and 9 using the quantum algorithm. You can see that if you have the NMR pick up, it indicates you have a handwriting 6. Otherwise, it means that your handwriting number is 9. I think this is probably the earliest one in this the experimental work in this quantum machine learning field. And in these slides, I'm gonna focus on this algorithm, quantum PCA, and I will also introduce our experimental work. Okay, first, let me introduce what is PCA algorithm. It was invented by Carl Pearson in 1901, and its category is under the unsupervised machine learning. The purpose of the PCA algorithm is to reduce the dimension of the classical data, and its procedure is through the orthogonal linear transformation. Now the PCA has a wide of applications in pattern recognition, image compression, and recommendations algorithm, and so on. I guess you may get confused, like, what's the essence of the PCA? I think the key idea of PCA is in this figure. The purpose is to reduce the dimension of the data. So suppose now you have the data in 3 dimensions. And what you do via the PCA is you find 2 axes. Now we call the axis the principal components. This is the first principal component. This is the second principal component. These 2 principal components are orthogonal to each other. So they form a 2D plane. Then you just project your original data onto this 2D plane. Then the original data becomes 1 dimension less from 3D to 2D. That is the realization of the dimensionality reduction. And the rule to find these 2 principal components is that you have to guarantee that the correlation between the data are minimal. That is, the variance of the distance from the data to the axis is maximum. The distance is maximum to reduce the correspondence between data as much as possible. So that's the purpose of PCA algorithm. And its basic procedure is like follows. There are in total 5 steps. First, suppose that you have m samples, and for each sample, it has n dimensional data. So in total, if one sample is represented by a n column vector, then the total data set is n by m. So this is the m samples, and for each sample, it has n dimensional data. Then what you do next is you recenter the data at the origin 0. That is, you use the original data x to minus their average x bar to recenter the data, and then you multiply x minus x bar with x minus x bar transpose. Then you got a covariance matrix. So you can think the x is n by m. So this guy is n by n. So the final output covariance matrix is n by n. That's the dimension. So it's an n by n matrix. So why we call that covariance matrix? Because in this C matrix, the diagonal elements means the variance of the dimension, and the off diagonal elements means the covariance between dimensions. So it captures the core data, the relation between dimensions of the original data set in this n by n C matrix. What you do next is you do eigen decomposition, and you put the eigenvalues of C in descending order. That means you diagonalize this covariance matrix and find all of its eigenvalues, lambda 1 to lambda n, and all the corresponding eigenvectors Q, where the first eigenvector is V1, the second is V2, and etc. Then what you do next? You pick out the principal component of the C matrix. That is, you just pick up the eigenvalues with the bigger numbers, the largest eigenvalues, and their corresponding eigenvectors. For example, you can pick the eigenvalues from lambda 1 to lambda k, where their eigenvectors is from V1 to Vk. Then you get a new projection matrix. You have omitted all the eigenvalues from k plus 1 to n, but you only keep the first k eigenvalues. So now the matrix after this eigen decomposition and the selection process, you only have p projection matrix with k by n. You know, here C is n by n, and now after you have omitted the eigenvalues from lambda k plus 1 to lambda n, you only have k by n left. Then what you do next, you just reduce the dimension of the data set by multiplying p with x minus x bar. You know, p is k by n, and x is, in the first step, is n by n. So the final dimension of the data set is k by n, which means you only keep the first k principal components of the data, and you project the original data set onto a k-dimensional subspace, which fulfills the task of dimensionality reduction. And you may find that during the 5 steps, which step can be sped up on a quantum computer? You may notice here from C to step 3, you have to do eigen decomposition. And the covariance matrix C is actually semi-definite positive because its form is like this. So it's semi-definite positive. So it's very similar to a quantum state rho up to some normalization factor. So you can think C may be represented by some quantum state rho. And what you do next, you have to diagonalize this state rho, where may lead to a quantum speedup. So that's where the quantum PCA comes from. I will show you a very simple example about PCA. Suppose that we want to do the user portrait analysis. We have a training data set, very small, with only 4 people, Jack, Tom, Mary, and Lucy. They have, you know, different sexes, different ages, incomes, marriage status, and Twitter followers. And we know that Jack and Tom are not the targeted users. Mary and Lucy are targeted users of our system. Then what we want to know is, I give you a new person, say Jerry. We know the Jerry's basic information. And I want to ask, is Jerry a targeted user or not? Okay, if you want to solve this problem, we can follow the steps of the PCA. What do we do first? We do data normalization. We normalize the sex, age, income, marriage status, and Twitter followers in this way. And all the original data set now are centered at 0. And the normalization factor is 1 now. That means the range is from -1 to +1. And what you do next is you calculate the covariance matrix C, and you will get this table, which is 5 by 5, because each sample here have 5 dimensions. So the final covariance matrix is 5 by 5. And these diagonal elements means the variance between the same dimension. And the off-diagonal element means covariance between the 2 dimensions, like here is age and sex. And what you do next, you decompose the C matrix and you put the eigenvalues in the descending order. You will find out that only lambda 1 and lambda 2 are big enough. So you only leave these 2 as the first 2 principal components. You discard all the other 3 and their eigenvectors. So now you have a projection matrix. The first one is an eigenvector of lambda 1. The second one is the eigenvector of lambda 2. Now you have the projection matrix. What you do next is you multiply this P matrix with the original data set. And you will find that for each person, for each user, they only have 2 dimensions left. You know, originally they have 5, but now they only have 2. And we can calculate the 2 dimensions for each of the user. And this is a new user, Jerry. And we have finished the dimension reduction. And next, you just plot the 2-norm distance between these 5 guys, you will find out that Jerry is closest to Jack. Because Jack is not the target user, either Tom is not the target user. So Jerry, who locates in the middle of the two, is highly possible to be not the target user. So that's the basic idea of the classical PCA. And the second part, so how to do quantum PCA? And here we use a tool called parameterized quantum circuit. So now we know the basic process for the classical PCA algorithm. If you want to put it onto the quantum computer, what you do first is you have to encode the covariance matrix C into some quantum state. This is semi-definite positive. This quantum state is also Hermitian and semi-definite positive. So there should be a map between the two. But the first problem, how to load classical data into quantum registers. That is how to build a quantum random access memory, a QRAM. Unfortunately, this is very hard. In 2008, there is a theoretical paper by these 3 guys. They propose an idea called bucket brigade architecture. From this one, you can efficiently realize a quantum RAM. But unfortunately, there are several caveats in the quantum RAM method, which disables its experimental implementation till now, which means there's no experiment in the QRAM field. So this step is very hard. Okay, the second problem is, suppose that you have loaded your classical data into a quantum state, then how to do the eigen decomposition of the quantum state rho? In 1999, also by Abrams and Lloyd, they propose a quantum algorithm which has exponential speed up to find the eigenvalues and eigenvectors of some matrix. But if you note the abstract, you will find out that this algorithm only works to find the eigenvalues and eigenvectors of a local Hamiltonian, not a state. Although Hamiltonian and states are both Hermitian, but Hamiltonian means you have the dynamics of a system. Rho is just some input data, so they are basically different. This algorithm only works for Hamiltonian, which you have dynamics, but we don't know how to do eigen decomposition of a state rho. Then you can try to think some way to map a state to a Hamiltonian, which means if you can realize the rho in the exponential term, if you can realize e to the minus I rho t, then rho behaves like a Hamiltonian. So problem 3 is how to realize e to the minus I rho t. In 2014, Lloyd again. So, I mentioned Lloyd so many times to show my respect. So I put his, picture here as a, handsome tomboy. In this paper, Lloyd and his colleagues propose an algorithm called quantum PCA. And the core idea is in this equation. Actually, this is the only equation in this paper. From this equation, we can see that if you have a state rho, tensor state sigma, if you do a e to the minus I s dot t, where s is a swap operator, what you have finally looks like to realize e to the minus I rho delta t applied on some state sigma and e to the I rho delta t. That means if you can repeatedly apply n copies of rho, then it allows one to construct the dynamics of the e to the minus I rho t. But it has drawbacks, in particular for experimental lists, because it requires multiple copies of rho, which is a loss of the space complexity. And it also requires quantum phase estimation, which is very difficult to perform in real experiments. Okay, so from now on, it's our algorithm. Let's go back to the eigen decomposition in the quantum principal component analysis. Back to problem 2, how to do eigen decomposition of a state rho. We can always write down rho in its eigenbasis like this, where we assume the lambda here is in the descending order from lambda 0 to lambda n minus 1. If you can find some unitary, let's call it UG, you go. If the UG can transform this rho to the computational basis, now the eigenvectors are in the computational basis from 0, 0, 0 to 1, 1, 1, Then we can diagonalize this rho. That means if you can find UG, you can diagonalize this rho in the computational basis. Then you just measure the computational basis, you can get lambda. Then you finished the eigen decomposition. So the problem now converts to how to find this operator UG. If you define some observable, let's say P, it's a Hermitian matrix, it's also diagonal matrix, and the diagonal elements are from 0, say, to n minus 1, which means all the diagonal elements are different. Actually, this P is quite simple. It's like this form. You just have sigma z for each qubit, and with some weight factor here. And for this observable, it's a Hermitian, it's a semi-definite positive, and its elements are 0 to n minus 1. Then we can prove that if you minimize this objective function L, that means you apply this U, that's UG that you want to get on this state, and you observe the P operator. If this guy is minimized, then we can prove that this U can diagonalize the state rho in the computational basis. The rigorous proof requires the Birkhoff von Neumann theorem and the rearrangement inequality. So I leave the details. I'm not going to talk about details here. So our problem now becomes how to minimize this L objective function with this operator. Then you need to utilize the parametrized quantum circuit. We call it PQC for short, and hybrid quantum classical control approach. Assume that you have some U theta, but you don't know its form. The target is to find some UG to minimize the objective function. But for any U theta, you can decompose this operator with PQC, like this one. So in this circuit, all the angles, rotating angles, are not determined. So what you do is you use some algorithm to iteratively run this circuit, and you minimize the objective function. And finally, you can get the rotating angles here. And how to do the iteration, you can use a hybrid quantum classical control, which means you initially guess some values for all the theta here, and you just run the circuit. You measure the objective function L. If it's not good enough, then you measure its gradient. You change your parameters theta here along the gradient function, along the gradient direction. And then you run the circuit again, you measure the L function. And if it's not good enough, you calculate the gradient again and just do the iteration. If L is minimized, it's very close to 0, then you say, oh yes, we have optimized this circuit. Then the task is done. So this is the way to optimize the PQC. We call it quantum classical control because here to run the circuit, to measure the objective function L, to measure the gradient are all finished on a quantum processor. But to update the values, to do the iterations, it's done on a classic computer. So it's a hybrid approach. So here gives a sub-algorithm of this quantum PCA via the PQC, the parameterized quantum circuit. I'll skip this slide. And the final part is about the experimental quantum PCA for face recognition. If we focus the problem of the PCA on the face recognition, that is, you give a training data set with many, many images. You train your computer, and finally you give another image of a person to the computer and asks, which person does this image belong to? And you want the computer to answer this question as correctly as it can. So how to do this? The first, you just to do the data pre-processing, and you pre-process the face image of a person into 100 by 100, say by 100 by 100 grayscale, and you reshape this image into a 10,000 by 1 vector. So this is done on a classical computer. Then if you have 4 images as a training data set, that means you have 4 different face images. So the total training data set is 10,000 by 4 matrix. That means the covariance matrix of this training data set is 10,000 by 10,000. The size is very big, and it's very slow to process even on a classical computer. Fortunately, in 1991, Turk and Pan proposed some new algorithm to do this face recognition. What they do is they don't calculate the covariance matrix by A transpose, but they calculate the matrix, they call that D, where D is a reverse order of A. That's A transpose times A. And it has eigenvalues lambda I and eigenvectors psi I. So you know that because A is 10,000 by 4, so the dimension of D is only 4 by 4, which is very small. Then why you can use D instead of the covariance matrix? Because if you apply D on the eigenstate, on its eigenstate, so and if you put A matrix at both sides of this eigenequation, you will find that AAT is C. You will find that C, A, the eigenstate, equals lambda I, A, the eigenstate. Which means if you calculate, you can calculate CA, you can call you call this psi, and this psi also has the same eigenstate as that of D. And this psi is called eigenface matrix. So that is why in this algorithm, the author said you can calculate D reversely, and it will greatly reduce the difficulty of this process. Then to implement the quantum PC algorithm, we use the NMR experiment. In NMR, you use a spin half nuclei as qubits. If you put the spin half nuclei, for example, the proton, the carbon-13 or fluorine-19 in magnetic field, the spin will be split into 2 energy levels. One is spin up, one is spin down. You can label spin up as 0 and spin down as 1. You can control the Rabi oscillation between the 2 energy levels by applying the radio frequency pulses. So that's a quantum processor. In this experiment, we use a 4-qubit quantum processor, which has 1 carbon-13 and 3 Florence. So it's a 4-qubit. And the experiment is carried out on a 600 megahertz NMR spectrometer. So in a nutshell, NMR experiments runs like this figure. So it's very complicated, but we can summarize the steps into 4. The first one is you sit before your computer and you just make your pulses, you make your sequence, you input the orders, and the next is the devices try to generate the radio frequency pulses as required. Then these pulses go into the magnet and have resonance with your sample. So the third step is resonance. And after resonance, the pulses carried the information of the dynamics of your sample. And then you receive the pulses and process the signals. So that's the basic procedure for an NMR experiment. And what we do in this experiment is we have 4 training images and 4 test images. They are from the yield phase dataset. So the steps are like this. First, we calculate the eigenphase matrix D, that's A transpose A. We have showed that the dimension of D is only 4 by 4, which means it's a 2-qubit quantum state. 4 by 4 is 2-qubit quantum state, but it's a mixed quantum state. In experiment, we prefer to start from a pure quantum state. Then we expand this 2-qubit mixed state into 4 qubits, where the the input state is now pure. So this is the initial state, psi D, which is a pure state, but its dimension is now 16 by 16. Then we perform the PQC, the parametrized circuits. We just use 2 layers to train the circuit. We put the initial guess, we measure the objective function and gradient. Because it's not good, so we go back and update the parameters theta. And we do this whole circuit again. We measure L and G, and we repeat these iterations by 10 times. And after 10 times, we find that L is already minimized, very close to 0. Then we think we are done. So we go, now we have the target UG. We just reversely apply UG dagger on the computational eigenstate. We get the eigenstate of the eigenphase matrix D. You know, the eigenstate, the dimension of the eigenstate is 4 by 1. Then from this D, and we apply A on this eigenstate psi j, then we get the eigenvectors of the covariance matrix AA transpose. That's the C matrix. We get the eigenvectors of the C matrix, and its dimension is 10,000 by 1. Then we compare the test data set with these eigenvectors and to find the minimum distance. So these are the iteration results. After 10 steps, you can see the objective function is minimized to almost 0, very close to the global minimum. And also after 10 iterations, we find that the eigenvalues of the eigenphase matrix approach their ideal values, which are labeled by the dashed line very closely. And the eigenvectors of the eigenphase matrix have almost close to 1 fidelity, which means the iterations are very precise. Then finally, we get the Kasai, which are the eigenphases of the 4 training images. You can see that this is the training data set, the 4 images. These are eigenphases. You can compare these 4, and you find out that each eigenphase image is consisting of many characteristics of the 4 images. Like this guy have beard now, and this guy, in this image, the mouth is like this. Then, after calculating the eigenphases, we just compute the weight vectors for each image in the training data set. We got the weight vectors for each training image, and we also get the vectors, weight vectors for each test image. And we compare the training vector and test vector using the 2-norm distance. And we find that, for example, this image has the minimum distance with this picture. So which means this person is him. And this image has a minimum distance with this picture. So the person is him. And this one has a minimum distance with this guy. So for now, our computer has finished the task of the face recognition. We also simulate different PQC models, like more complicated with auto connectivity. We also simulate more layers, like in this picture, we simulate 1 layer, 2 layers, and 5 layers. In fact, we simulated up to 20 layers. And we find that if you have more layers in simulation, the quantum algorithm will be more and more precise, which is consistent with our prediction. Okay, here is a summary. So we propose a new quantum PC approach where the parameterized quantum circuit, we don't need the multiple copies of the quantum states. We don't need the quantum phase estimation either. And in experiment, we do a proof of principle NMR experiment for 2 images to implement the task of face recognition. And the open problem is how to efficiently encode the classical data into the quantum states. That is, how to do a quantum RAM is still open. I guess for now, no people know how to do this step. I would like to thank Dr. Tao Xin, and he performed the experiment, and Dr. Ying Dou, and when he came to my university, so he designed the quantum algorithm for the PCA, and my PhD student, Liang Yuche, he is from computer science department. So he provides us the basic steps of the PCA and face recognition. I would also like to thank my funding agencies. Okay, that's all. Thank you so much.
Thank you very much, Dr. Davai Li, for a very clear presentation. Now I would like to request the audience, if they have some question, please raise their hand. I see one hand, Professor Kavita Dorai. So can you please unmute yourself and place the question?
Yeah, thanks. Am I audible?
Yes. Go ahead, please.
Yeah.
So Davai, great to listen to you. It was a lovely talk and a very nice experimental results.
Thank you so much.
I have a couple of questions. One, of course, is about the 4-qubit pseudo-pure state. So, what kind of fidelities were you able to achieve? And the second question is, obviously you must be having a hugely horrific pulse sequence. So did you have to worry about decoherence during the application of the pulses, and did you have to apply some kind of protection to cope with the decoherence?
Okay, thank you, Professor Darai. So I will answer your 2 questions one by one. The first one is you ask, because in this experiment, we have to prepare the 4-qubit pseudo-pure state. That is all 0 here. Actually, we have evaluated the fidelity for this 4-qubit pseudo-pure state, and it's always over 99%. Because we work a lot with this sample, and we have good control of this sample, and the fidelity, I think it's good enough. And the second one is about the very long sequence for this parameterized quantum circuit. In fact, it's not a long sequence, because from here, this is not a sketch of the sequence. It's a real sequence. You can see that we only apply a single qubit rotation on the first spin, the carbon-13, and another single qubit rotation on the second spin. So they are easy, right? Just hard IF pulse, not hard, but soft IF pulses. And then we apply a C0 gate consequently. And the C0 gate is a typical gate in the experiment. And we only repeat this parameterized circuit twice because we only have 2 layers in experiment. So you can think that the total sequence for this experiment only consists of 4 single qubit rotations and 2 CNOT gates. So it's not long compared to the coherence time of the spins here. So we can omit this sequence time.
Okay, wonderful. I couldn't believe it. I actually thought that you had a whole huge sequence hidden between that, behind that.
I wish
thank
to.
you so
But that's why we only choose 4 images here, because it can be 4 images means a 4x4 matrix. It only requires 2 qubits. We use 4 qubits here just because of this 2 qubit state is a mixed state. We want to start from a pure state so that we expand this 2x2 mixed state onto a 4x4 pure state. But the following operations only need to apply on these 2 qubits because we don't need these 2.
Okay, thank you.
Okay, thank you.
So is there any other question from the audience? You can also write on the chat box. Yes, Professor Usha Devi. So please unmute yourself and place the question.
Thanks for a very clear talk. I enjoyed this talk. So I just wanted to know this NMR experiment that is done. This is a quantum experiment. But if you had a classical analog of this, would you be able to kind of identify what is the ratio of kind of advantage using quantum system? Is it done?
That's a very good question, and that's critical actually. I think, frankly speaking, the answer is no. Like, we don't exhibit any quantum speed up in this proof of principle experiment. And I think the critical problem is just like I mentioned in the second part, the problem 1. How to load the classical data into quantum registers. I have omitted this question. I start from a quantum state saying that this quantum state has incorporated my classical data, but in fact, this step is very hard. There are no efficient methods, at least in experiment, to encode the classical data. If you cannot do this, complex loading step will rule out all the quantum speed up of this algorithm. But I just say that this is not our focus. So we have omitted this problem. But if I want to answer your question strictly, I think there's no advantage beyond the classical one due to this QRAM inefficiency.
Okay, thank you.
Okay, so I see no question coming from the audience. So, okay, so for that, let's thanks once again, Dr. Dawai Lu, for this wonderful talk and the discussion. Thank you very much. Now I will request you to unshare your slide.
Okay.
Thank you. With this, we go towards the second talk of this session. So our speaker will be Professor Guru Prasad Kar. So let me say a few words to introduce him. So Professor Kar has received his PhD degree from Calcutta University in 1997. Then he joined as a faculty member at Indian Statistical Institute, Kolkata in 1999, and has been a professor at ISI, that means Indian Statistical Institute in Kolkata, since 2012. His major area of research is foundations of quantum mechanics. Today he will be talking on perfect quantum communication with useless channels by using quantum switch. Now I would request Professor Guru Prasad Kaur to start the talk. It's over to you, Professor Kaur. Yeah.
Do you see my slide, Manavendra?
Yes, we can see your slide, but we don't see your face clearly. Can you please?
Or maybe because of
Yeah.
the height of the table.
Yes, yes, yes. Yeah, now
Thank
it's
you,
better.
Yeah.
Now it's better. Please go ahead.
Yeah. Thank you, Manavendra, for the introduction, and thank all the organizers at ISAR Mohali. And also, I'm anxious that the day we are holding this conference, we are participating in this conference. There are thousands of farmers sitting on the road in the cold with their justified demand, but somehow we have to run this conference because it is an international conference, and I hope justice will prevail and an amicable solution will be reached very soon. Anyway, let us come to our talk. This talk is based on a paper in archive. You can see it. This indefinite causal order enables perfect quantum communication when the capacity of the channel is quantum capacity of the channel is 0. The main idea came from actually Dr. Manik Bonik, and then through this collaboration with many guys, including me, the final form came. So let me start. So Shannon theorem already we know that if you are given even a bad channel, which is not a perfect channel, so we know how to calculate the capacity of that channel because we can calculate the mutual information, and we know how to get the capacity. We have to maximize over these inputs. We have to maximize this mutual information. So with this formula, if there is some correlation between input and output, this is a great discovery by Shannon. If there is some correlation between input and output, capacity is non-zero, implying faithful transformation. Now, when you come over to quantum mechanics, so you have to define a quantum channel, and quantum channel actually can be defined. As defined by Krauss, that this channel acts on a given state rho, which is an input, and you finally get this output where EI is the operator, and this satisfies this condition. And also Krauss also showed that it can be realized via some extra system and extra ancillary system, which you can call environment, and you can realize it as a unitary operation over the whole system and then trace out the environment system. You get the action of this quantum channel on the state rho. Now, what about the capacity of quantum channel? When we tell about capacity of the quantum channel, actually, you have three kinds of capacity of quantum channel. One is classical capacity, another is private capacity, and another is quantum capacity. So three types of capacity for quantum channel, but here I am not going to discuss about private capacity. So classical capacity already we know that how to calculate it. Its calculation is based on finding this quantity, which is called Holevo quantity, and you have to maximize over all inputs, all possible inputs, and you get the classical capacity. Analogously, you can have a formula for quantum capacity also. For quantum capacity, it was most possibly in 1997. It was first given by two groups. One is Lloyd, another is, I forgot the name. Not Devetak, some Schumacher, most possibly. And so actually, you have to find the coherent information of a channel, which is defined in this way, where R is a reference system here. And Schumacher also proved that if you send a quantum particle through this quantum channel realized by these overall unitary operators, then condition that this error that occurred to the quantum system, it can be corrected if this initial von Neumann entropy of this system is equal to the coherent information. And based on this thing, whatever error has happened, you can correct it if this condition is satisfied. This is necessary and sufficient condition. And based on this thing, actually quantum capacity has been defined. So quantum capacity, I'm not going into the details since mainly coherent information, but sometimes we have to take the asymptotic limit because this may not be additive. And so quantum capacity is just maximizing this coherent information. Now we are coming to a point where you will see how that miracle that we know because of superposition of path in quantum mechanics, because this is a miracle, because you are sending photon with this arrangement where this is 50% beam splitter, this is again 50% beam splitter, and we know that if photon is sent one by one, our common sense or classical ideas tells that 50% photon should have gone there and 50% here, but it happens that all the photon is coming to this detector D2, no photons is going to D1. Now we are coming to a peculiar situation where you can also, here it is actually superposition of path here, but you can make superposition of order of channels. So if we consider two quantum channels, one is E and the other is F, and a quantum system, let it is sent, first it encounters channel E and then it encounters F, it may happen. But it may also designed in this way that quantum system first encounters F and then encounters C. So in our classical way of thinking, we can think that photon can be sent in this fashion, or photon can be sent in this fashion, or photon can be sent as a mixture of these two. But using quantum superposition, you can have another situation where you will have indefinite causal order. To see how this thing acts, let us see an example. This example was given in a paper by Buchner groups in 2014. You see that how it can be implemented, and you see how power of this indefinite causal order can be achieved. This is also named as quantum switch. Most possibly this idea of quantum switch was introduced by Chirivella, who is also one of the author of this paper. So you consider this arrangement. This is polarization sensitive beam splitter, two polarization beam splitter, and this is some unitary operation U1 and this is some unitary operation U2. But for the general channel also you could put some quantum channel here, E, and another quantum channel F here also. Now, this has been designed in such a way that if the photon is sent when the photon initial state is 0C, that means it is horizontally polarized, then actually the photon passes. And also we are considering, let me tell you, we are considering the photon's polarization degrees of freedom and some other internal degrees of freedom represented by this state psi. So it has another degrees of freedom on which this unitary operator U1 or U2 will act. Now, if the photon is initially horizontally polarized, then if you send this photon will come and transmitted through this first beam splitter. Then it will encounter this unitary operator U1, then it will come out, and then again it will be transmitted, and it is somehow by some arrangement it will be taken back, and again it will come to the first beam splitter, again it will be transmitted, and it will encounter this unitary operator U2, then come out and then transmitted, and you get it. So if the initial state of the photon is 0C, that means it is horizontally polarized, then final action is something like this on the other degrees of freedom. So U1 act first, then U2. But instead, if the photon is vertically polarized, then it will be reflected in both the beam splitter, and you can follow the path, and you will see that U2 will act first, then U1 will act. Oh, by mistake, I have put here 0C, it will be 1C. It is vertically polarized photon. But interestingly, when you put the photon not polarized vertically or horizontally, but as a linear superposition of them, say alpha 0 plus beta 1, then actually the whole thing, when the photon will come out, the action that will you have on other degrees of freedom, I mean on psi, it will be alpha 0 U2 U1 psi plus beta 1 U1 U2 psi. Now, if you measure this polarization degrees of freedom in the 0-1 basis, then there is no miracle. Because either you will collapse on 0 or you collapse on 1. So it happens that either U2 U1 act on psi or U1 U2 acts on psi. But instead of that, you can also make measurements in other bases. Now, as I was telling you, that to see the power of this quantum switch, you design a problem. Let this one of these thing is correct. One of these thing is true. Either commutator acting on psi, commutator of U1 U2 acting on psi is equal to 0, or anti-commutator of U1 U2 acting on psi is 0. You have to verify which one is true. Now, if your initial state, which we took here as alpha 0 beta 1, if you make it 1 by root 2 0 plus 1 by root 2 1 for its polarization degrees of freedom, and you send the photon through this setup, finally what you get this thing. Or finally you get this thing. Now you see, if this is true, and if you measure the particle, I mean measure the polarization degrees of freedom in the plus minus basis, if this is true, then always you will collapse on minus, and you will know that this is 0. I mean this is true. And if you collapses on plus, then you know that this is true, because that term has disappeared. So measurement in this basis will resolve the question. But if you want to resolve this question without using this quantum switch, then it has been shown by Chirivella and his co-authors that at least one of the gates has to be used more than one time, I mean, more than once. But here, using this circuit, actually you can determine by just one go whether this is true or that is true. So this somehow shows the power of this quantum switch. Now, we can consider in general two quantum channels, channel E and channel F, which is defined in this way. Now, if you again switch, if we use quantum switch, I mean quantum switching of their orders or indefiniteness of their causal order, then these Krauss elements for the switched channel will be in general will take this form EIFJ tensor. This is this control bit, for which in our earlier example we use the polarization degrees of freedom, but here it is in abstract sense that this is this control qubit, and this is this quantum operations And in general, for the if these two with this two quantum operation, if you use this quantum switch, then in general these Gauss elements will be like this. So if you consider this your quantum system that pass through this combined channel, and if the state of this control bit is initial state of the control Q bit is omega, then as a whole the quantum operation will be realized in this fashion. With using this thing, actually Chirivella and his group showed that even if you have some quantum channel which is useless, which is useless means if its classical capacity is even 0, then using quantum switch you can make this classical capacity to be non-zero. So for that, they actually considered completely polarizing channel. That means this classical capacity of this channel is 0. Then switching these two polarizing channels, so they take two depolarizing channel and using the quantum switch, and applying these operations, as I told you, applying this operation, they showed that and they find this Kij, and they showed that this final state will be something like this. And if on the control qubit, instead of measuring in the 0-1 basis, if you measure in the plus minus basis, then final state will not be identity. Because if you consider two bad channels and if you use them consecutively, if their classical capacity is 0 for both the channel, if you use consecutively this kind of channel, still this classical capacity will remain 0. But here you can see if you collapse on the control bit, if you collapses on plus, then this state is this. So not all the information of initial state is lost. There is some information about the initial state. Even when you collapse on minus, then also there is some information about the state. So as I told you, if there is some information of the state in the final state, then classical capacity is always non-zero. And actually, Chirivella et al. In their PRL paper, they actually calculated this classical capacity of this completely useless channel. They showed that if you use quantum switch, it is non-zero, but they gave a closed formula at least for their thing. But here I am trying to emphasize that it is actually non-zero. Individually, their classical capacity for both are 0, but if you switch them in this fashion, then classical capacity is non-zero. Then actually we were thinking that, okay, this is very good result, but if we take two channels whose quantum capacity, whose classical capacity may not be 0, but whose quantum capacity is 0, then if we switch them, will we get quantum capacity which is non-zero? So this was our motive. For that, we started with a channel like this, which is a general polarizing channel, which is, I mean, all the terms are there. And so it is a depolarizing channel, and if you switch them, it actually, this, if I use this Gauss operator and find this thing, it will be a big thing. So it has been written in a short way, where actually C plus rho is equal to actually this thing, and plus this thing, and C minus rho is this expression are very complicated because we have considered all the terms. No, all the 4 terms here appearing here. And Q plus is this, and Q minus is this, and omega plus is omega, and omega minus is Z omega Z. But now we are considering this. So this is the general expression. So we come to a very simple case. Consider this channel. So consider a channel for which P0 is equal to 0, P3 is equal to 0. That means P1 and P1 is equal to P2 is equal to half. So this is a very simple channel. So acting on the channel, acting on rho, this final state is this. So this is a very simple channel, and this channel can be realized in many ways. But to tell that it is entanglement breaking channel, sometimes I use this thing, that actually, if you consider a teleportation protocol through a maximally entangled state phi plus and use this protocol, but instead of that, if your actually shared state is psi plus, then actually if you teleport them using the exact teleportation protocol for phi plus, then actually will not get rho will not be perfectly teleported, but rho will be rotated by sigma x. Similarly, through this channel, if you teleport a quantum bit using the perfect teleportation protocol for phi plus, then the state that you will get finally will be rotated by y. So if you use the convex combination of these two channels with equal weight, then actually, I mean, you could teleport a state through this kind of convex combination of these two Bell state, then your final state will be like this. It will be realized in this. But you can look at this thing that this is equal mixture of two Bell states. So actually it is a separable state. And by using a teleportation through a separable state, you can never send quantum information. That means it is an entanglement breaking channel. So its quantum capacity is 0. But at the same time, you can see its classical capacity is not only non-zero, it is actually 1, because you can use 0 or 1 and you can send them exactly. So classical capacity of this channel is 1, whereas quantum capacity is 0. Now we are going to switch this kind of two channels and let's see what happens. So hence for these channels, classical capacity is non-zero and quantum capacity is 0. Now we start our initial state of this control qubit. We take plus. Now you can, sorry. So if I put this thing that this P0, P3 are both 0 and P1 is equal to P2 is equal to half, using all these things and taking initial state of the control bit to be 0 plus 1 by root 2, I mean plus state. If you measure the ancilla in this basis, if you collapses on plus, then exactly the quantum qubit is remain intact. I mean, it's perfectly teleported. If you collapses on minus, then actually it is rotated by sigma z. So if you put, after getting this classical information about the measurement result, you apply sigma z and you get exactly rho. So communication will help construct exact quantum state. So what we did, we took two useless quantum channel and used them in their indefinite causal order. I mean, you use them combine them in a quantum switched form, and we send a arbitrary quantum state, and we see that after having this information about this measurement on this ancilla, result of the measurement on this ancilla, we can perfectly get the qubit state. That means for this quantum capacity of this switched to useless channel is 1. This is very, very powerful results. Even in classical capacity that I showed you in Chirivela's case, that classical capacity was not 1. But here we have taken two channels whose quantum capacity is 0, but their switched capacity becomes 1. I mean, perfect. That's why this is so surprising result. Of course, let me tell you that if you ask me what is the capacity, already we discussed what is the capacity of this classical capacity of this two channel. In our case, at least it is 1. But if you see this theorem, let E be a qubit channel whose quantum capacity is 0. Then for this two channel, if you switch these two channels, and if its quantum capacity is 1 for some state for some for some state of the control qubit, then if it is true, then there exists a basis in which the channel acts in this form. And actually we took the channel in this form, which is an entanglement breaking channel, but actually all the channels for which this quantum capacity will be 1, the channel must be of this form. So it also tells in some other way that you can, if you want to have quantum capacity to be equal to 1, then form of the channel should be like this and its classical capacity will be 1. So most possibly it is also true that to get quantum capacity to be 1 by using otherwise useless channel, most possibly their classical capacity should be 1. And there is another theorem in that paper. For every pair of complete eraser channel, E0 and F0, and for whatever state you choose for this control bit, the switch channel will be entanglement breaking. That means if you consider eraser channel, that means whose classical capacity is also 0, you can never have a channel with non-zero quantum capacity. I mean, so its classical capacity has to be non-zero at least. So theorem 3 establishes a complementarity between the activation of the quantum capacity and the activation of the classical capacity. Every channel that exhibits activation of the classical capacity, I mean from 0 to non-zero, does not exhibit activation of quantum capacity. With these two theorems, actually, I could have concluded my talk, but now, after this work, there had been many debates and discussions and many new papers. And there had been big debate also, because there was a paper, most possibly by Brankier and his collaborators, that without using quantum switch, if you put this quantum channel in linear, I mean superposition in the path, if you use this useless channel in this fashion, then also it provides some activation of quantum capacity. But it has been, they have seen that, of course, there is, though this quantum capacity of both this channel is 0, quantum capacity is non-zero, but that quantum capacity cannot be 1. But of course, it is non-zero quantum capacity with this arrangement. But later, this Bruckner et al., Bruckner and his group, they actually showed that, of course, to get quantum capacity to be equal to 1, you need not always have to causal indefiniteness. I mean, you need not use quantum switch. You can use them in a perfect, in a order, I mean, in a given order, like F, E channel E acts first, F acts second, but there is some other unitary operator acting through this, channel and the system between the channel. In this way, there is some arrangement, which is a very complicated arrangement, but they showed that again, with this combination, where you don't use quantum switch, there also you can get full activation of quantum capacity. So indefinite causality may not be a necessity for activation. This was their conclusion. Superposition of direct pure process may also work. After that, actually, Manik-Bonik et al. Recently devised another protocol for a quantum information processing task, which is known as random receiver quantum communication, where they have shown that this quantum switching has some advantage over this kind of superposition of channels. So here the task is something like this. Sender A wants to transmit a quantum message to one of the n spatially separated receivers, which is Bob 1, Bob 2, Bob up to Bob n. The identity of the targeted receiver X is unknown to the sender. So sender does not know where this unknown quantum state that is in Andy's lab has to be prepared that he does not know at which Bob's laboratory the unknown state has to be prepared. But it is known to the receivers. I mean, it is known to all the Bobs. And receivers are also allowed to collaborate through classical messages, but quantum communication among them is forbidden. Whether this task can be performed using quantum switch. Of course, if Alice shares E bits with each Bob 1, Bob 2, up to Bob n, of course this can be performed. This task can be performed, but this can also be performed if you use this channel. Sorry, what happens? Yeah. Yeah. What you do, if Alice share a switch channel of these two useless channel with each Bob, with Bob 1 separately, with Bob 1, Bob 2, Bob n, where this channel is nothing but switch channels of this XY, these two useless channel with this controller. If Alice share this channel with each Bob, then already you know it is a trivial implementation using quantum switch to perform this task, because already we know all these channels are perfect channels. All these is perfect channels, so Alice can encode this state in n qubits and send each qubit through these channels, and after that all these Bob, by their cooperation, I mean by making some measurement and conveying classical information, they can create the unknown quantum state in one of the Bob's lab they desire. So this is trivial implementation using quantum switch, but this Bonik et al., they have shown that this can also be done by just using one quantum switch. By just one quantum switch, and the same quantum switch is used for each circuit. This is, and all AI/BI is just this useless channel EXY. And using this one circuit, they have shown that this task can be performed. I mean, Alice does not know, but in which lab the quantum state has to be prepared, but using this thing, using this quantum switch and conveying the results on this control qubit to all the Bobs, this unknown state can be prepared in one of the Bob's lab by using just one control bit. And this one control bit is sufficient, and they have also shown that it is not possible, which may not be the case for superposition of direct pure process. So most possibly Bruckner tried to conclude in one of his paper that whatever advantage we can get from this quantum switch, this can be achieved by some complicated arrangement, but some kind of superposition of these two bad channels. So quantum switch is not a necessity, but using this channel, it is shown that just one control qubit is sufficient to perform this task. But if you take their circuit, then for each case you have to use one control bit. So for this task, if you use their circuit, n number of control bit has to be used, but here one control bit is sufficient to perform this task. Thank you. I think I have finished in time. Thank you. Thank you all for patient hearing.
Thank you, Professor Guru Prasad Kaur. It was a fantastic talk. Now I will request the audience, if they have some question, please unmute yourself. You first raise your hand, and then one by one, please place the questions.
And Manavendra, also I have requested Dr. Manik Bonik to be present in this talk, because the latter part that I told, actually I am not involved in this work, but
I see Manik is there.
Yeah.
Okay.
Yeah.
So is there a question coming from the audience? Please raise your hand. Okay, I don't see a question coming from the audience. Maybe I ask one question.
Yeah.
So all these discussions you made here,
Yeah.
are they specifically for these Pauli channels, in particular the ones that breaks entanglement?
Yeah, let me come to this theorem. If you want perfect quantum communication, then there exists a basis in which the channel looks like this. So classical capacity is also one.
Okay. Okay, thank you. So I see one hand raised. This is coming from Thomas. So Thomas, can you please unmute yourself and place the question directly?
Sure. Thank you very much, Chairman. So hello, Professor Carr.
Yeah, nice to hear you.
Nice to see you again. So I really enjoyed this inspiring talk. I have to think a lot about it, and I discovered some nice, way of using the Choi-Yamaokovsky isomorphism you mentioned here. So my first question is concerning this, that you are saying that if you have these erasure channels, excuse my English, erasure channels, and you use a quantum switch on them, then you get a entanglement breaking channel, right?
Yeah.
My question is, since so is it also possible to work with partial erasure channels and then get kind of a reduction of entanglement? So I wonder whether one can play around with trying to find some channels that are not directly entanglement breaking, but they can, since we know that there is only that that there is always a state that corresponds to the channel, an entangled state that corresponds to the channel, and the entanglement of that can be continuous between 0 and 1, and so I wonder whether there is something like this.
So this is a new area which is emerging, and I think instead of using this kind of channel, you can use many kind of channel which is not completely erasure channel, and maybe we can check. Maybe sometimes this is the theorem which tells if you finally want perfect channel, then form of the channel has to be of this form. But if you use other channels which is not erasure channel and quantum switch it, maybe you get some. Just before our Chiribella also provided some example. Yeah. So of course you may have some quantum capacity between 0 and 1. So it will not be in general entanglement breaking. So I mean, Swiss channel will not be entanglement breaking.
I see. Okay, thank you. And maybe my second question would be, is there some way of using this for QKD directly? I mean, can you invent some QKD protocol that is based on this?
Of course, BB84 can be implemented because this becomes Swiss channel is the perfect channel, but whether more involved process can be discovered using this quantum switch, that I have to think over.
Okay. Good. Then I thank you very much, and
thank you.
Thank you very much for this talk. Thank you.
Thank you, Thomas, and thank you, Guruda. So is there more question coming from the audience? We may take one more question if they are there. Okay, I don't see any question from the audience. So then let us thanks once again, Professor Guru Prasad Kaur for this interesting talk and for the discussion as well. So with this, we will actually go towards the next talk. Meanwhile, I will request Professor Guru Prasad Kaur to unshare the talk so that our next speaker can share. So our next speaker is Dr. Sudhir Shenthil. Let me introduce him quickly. Dr. Shenthil did his MSc and PhD from Indian Institute of Technology, Madras, Chennai. He is currently a faculty member in the Indian Institute of Space Science and Technology, Thiruvananthapuram, since 2010. His research area is quantum information, quantum computation, quantum optics, nonlinear dynamics, and chaos. Today, he will be talking on ergodicity in quantum systems. With this, I will request Dr. Senthil to start the talk. It's over to you, Dr. Senthil.
Yeah. Thank you, Dr. Manabendra, for the introduction. So I thank the organizers for inviting me to this conference. So today I will be talking about ergodicity in quantum systems. Yeah, so all of you know that if you look at the classical dynamical systems, there exist various ways to quantify, okay, or qualify the dynamical properties like periodicity, quasi-periodicity, ergodicity, chaotic behavior in classical systems. So this in classical system there exists randomness ranging from mere ergodicity to fully developed chaos also. If you look at classical systems, actually the necessary condition for classical dynamical system to show chaos is that the equation governing the system should be nonlinear. But when we go from the classical systems to a quantum dynamical system, all of us know that basic equation governing the evolution is the Schrodinger equation. So in this case, it is not straightforward to access the extent of randomness in quantum system. Yeah, so there are various non-classical features also happens when there is a time evolution happens in quantum systems. So like squeezing, wave packet revival, entanglement. So so many kinds of non-classical features also occur when a quantum system evolves under Hamiltonian. So for example, consider a simple one-dimensional example, which were a particle of mass m subject to a potential V of x. So we can write down the evolution of a state in that Hilbert space under the governing Hamiltonian H. Then we can, if the Hamiltonian is time independent, we can easily write down the solution for this. And basically the ket psi t is basically equal to e power minus iht by h cross ket psi 0. So right now I am not looking at any decoherence or any interaction with environment or any other such phenomena. Right now it is a simple evolution under a Hamiltonian. So here in this case, if you take any operator which is in that Hilbert space, we can find out the time evolution of that operator or the time evolution of the expectation value of some operator using the time evolved state. So that is basically the average A is you can calculate easily using this psi of t given here. Now, the Heisenberg equation of motion for any observable, we can easily write it as dA by dt, which is equal to this. And the Herrenfuss theorem states that we can write down these two equations, equation 1 and 2. But for quadratic Hamiltonians, we can easily write down this equation 2 in the form of equation 3. And that if you look at now equation 1 and 3, they actually, you can see that expectation x and expectation p evolves like a classical motion, or it looks like a Newton's equation. But in general, it is not easy, it is not possible to approximate any Hamiltonian into a quadratic Hamiltonian. So we may not get this Ehrenfest theorem, which actually gives the equation 1 and 3. So when Hamiltonian changes, you can expect a lot of different dynamics. Also, different kinds of non-classical phenomena can occur. And if you look at the quantum dynamical system in contrast to the classical system, basically the wave function, if you want to describe the wave function it's actually the probability distribution. If you want to look at, you need the infinite moments or expectation values of infinite operators to completely understand the particular wave function. So because of that reason, because in classical system, we understand that if it's a two-dimensional system, if there is only in three-dimensional phase space, there are 6 variables we have to look at. But in this case, you can see that any simple system have an infinite dimensional phase space. So the phase space picture also not that clear when we go to the quantum dynamical system. To understand the chaos or the nonlinearity in quantum system, there are various methods employed different people. One is to look at a classically chaotic system and quantize it, then find out in the classical limit what happens to the when there is some dynamical feature happening in chaotic system or the classical system, what happens into the quantum system. So, but it is not always easy to find a limit of the quantum system to get some classical counterpart. So in this talk, mainly I will be, actually I will cover various things. So here what we are actually looking at is, we consider the expectation, the values or average values as our dynamical variables. Like in classical system, we have the X position momentum like that. Like here also we consider the expectation values as our dynamical variables, and from the time series of the dynamical variables, we try to understand the quantum system and see whether we can get whatever we see in the classical system, like periodic. Anyway, we know that so many quantum systems shows periodicity, but like a quasi-periodic, ergodic, and chaotic behavior in quantum system. So this is our method of understanding the system. So here, if you look at the wave packet revival, so wave packet revival, so what basically happening is, so initially there is a wave packet, so there is some Hamiltonian which governs the dynamics. So under that Hamiltonian, basically for wave packet revival has to happen, there should be a collapse. So the Hamiltonian should be a nonlinear Hamiltonian. Then collapse happens, and later on the wave packet comes back to the initial state itself. So that is what basically the wave packet revival means. So in that case, the fidelity or the overlap function becomes unity, and we can say that there is a revival. So at these instances, what happens to the expectation values? So the expectation values return to the initial values so I call this revival time as T-rev. So at these instances, all the expectation value, whatever expectation values we can think about in that Hilbert space. So then for that quantum system, all these expectation values comes back to its initial value. So in a classical phase space, suppose we draw a classical phase space here, because we draw a phase space here where this expectation value are the dynamical variables. The trajectory is a periodic orbit with the periodic T-rev. So just to have some understanding about that, so for this purpose, what we consider is the initial coherent state, and which anyway, all of you know the definition, which is the eigenstate of the operator A, and which can have this Fock state representation. And for this particular purpose, we consider a Kerr medium. So a Kerr medium modeled as a single one-dimensional quantum system, where the Hamiltonian is a dagger square A square. So that can be written as n into n minus n1, where n is a dagger A. So under this Hamiltonian, using the periodic properties of the unitary time evolution operator, we will be able to write down gets IT at any instance of time. And we can easily show that at certain intervals like t is equal to t rev, that is basically here pi by chi, there is a revival. Also, there exists another interesting phenomena here, which is called fractional revivals. In that case, what happens is suppose in this case pi by chi is the revival time, and pi by k chi for k is greater than 1, where k is an integer. So there is in between t equal to 0 and the revival time, there is a fractional revival occurs at pi by chi. At this instance of fractional revival, the wave packet splits into different initial superposition of the initial states. Okay, so it is actually like initially when time evolves, the system spreads. Then suddenly you can see a couple of means in the phase space. If you plot whether Wagner function or Q distribution, if you plot, you can see that it splits up into 2, 4, 6 kind of wave packets in phase space, and that is actually the wave packet fractional revival. So our interest is about the revival here. So if you look at the average value x and x square, we can see that at the revival time, that is t by t rev is plotted, so it exactly comes back to the initial state. You can see the periodicity here. So this system where the Kerr medium modeled by a dagger square a square, which actually shows a periodic quantum dynamic system. So irrespective of the state you consider in this case, whether it is a coherent state or a skew state or photon added coherent state or any kind of state you consider here, all these states under this Hamiltonian show a periodic orbit in the phase space. So this is very interesting. But another thing is that suppose if we change the initial state, periodicity will be there, but period of the oscillations will change. That anyway I will talk at the end of this talk, today's talk. So period may change, but the periodic property will not change. It will not go to any other dynamical properties. So now we have already seen the periodic thing. So now let us look at whether we can get something non-periodic. So for that, we actually explicitly model this system, which is basically a electromagnetic radiation interacting with a medium, with B corresponds to the atom and A corresponds to the field. So this is actually nonlinear. So there is a nonlinear part and there is a interaction part. And you can clearly see that in this case, obviously there is an interaction happening. So there is a chance for the entanglement also. So here, when suppose we consider different kinds, so we can consider different kinds of initial states for the incoming electromagnetic radiation. So it can be a Fock state or coherent state or M photon coherent state. So then we can also calculate the entanglement in this system because it is a closed system. We can von Neumann entropy is more than enough to calculate the entanglement, to quantify the entanglement, or subsystem linear entropy we can calculate. So when you look at from the entanglement side, so what you can see that if this gamma by G, which is equal to 0.01, that means you have a very small nonlinearity, then for the initial state, that is atom is in the field is initially in the 10 photon state and atom is in the ground state. Second case is the atom is in the ground state and the incoming radiation field is a coherent state. So you can see that this entropy or the entanglement measure, you can see that for a very small nonlinearity and then nu equal to 1, you can see that both of them actually shows some kind of periodic nature. So if you plot this for a larger time, this keep on repeating. But if you closely watch this graph at t is equal to gt is equal to say 600 plus, it actually does not come back to the initial state. So it is actually something like a near periodic, or something you can talk about is a quasi-periodic. So exact periodicity does not happen in this system. So this is based on the entropy plot. So if you increase the this value of the state you are taking, and it's for the average photon number, you can see that such kind of behavior, that coming back to the initial state, very close to the initial state, also does not happen. So in this case, there is a situation, the system comes back to very close to the initial state. There is also a situation when increase the nonlinearity, it actually does not come back to the initial state, so that there is a possibility of getting an ergodic orbit or chaotic orbit in this situation. So we studied this further, and basically looking at the certain dynamical variables in this system, and considered this dynamical variables expectation values as time series. So we have calculated the first return time distribution, recurrence plots, Lyapunov exponents, power spectra, all these things to identify whether we can see any kind of chaotic or ergodic behavior in the system. So that was our aim in this case. So for this time series analysis, I'm not getting into the details of how to perform a time series analysis. Basically, so here the average photon number is considered as a dynamical variable, and then we use the phase space reconstruction. So that, see, in principle it is infinite dimensional phase space, but I can start with the one, because in the dynamical theory, the dynamical system theory, there is basically, if I have a one time series available, I can actually reconstruct the phase space. Using that reconstructed phase space, I can calculate the whatever the quantity which actually will tell you whether there is a chaos or not. So like a Lyapunov exponent or any other quantity, we can easily calculate from this. So this is the analysis we have done. So this is basically, I am changing the initial the state for the electromagnetic radiation from alpha to alpha comma 5. So alpha comma 5 is the 5 photon added coherent state. So alpha comma 1 is a 1 photon added coherent state. So already this alpha comma 1 has been produced in the lab. So producing this photon added coherent state is a difficult task. So I think people are still trying to produce this higher order photon added coherent state, which is actually a non-classical state. Ket alpha, because is a classical state, and the photon added coherent state is a non-classical state. So if you look at from to this side, this is basically increasing the non-classicality. And if you go from this top to down, it is like increasing the non-linearity. So what our analysis shows that if my nonlinearity is very small and the initial state is very far from the non-classical state, so we get a regular behavior. So all these things are regular behavior, but when I increase the nonlinearity, I can see that there is a positive Lyapunov exponent coming into the picture. So this is so for large nonlinearity, you can see that there is all the states, whether the field is in the coherent state or photon added coherent state, it does not matter. You get everything actually chaotic behavior. So that was just one system. So to get some features like this. So now we have moved to a system where you don't need the nonlinearity in terms of the Hamiltonian, but if you write down the Hamiltonian, it may looks like it is a linear because A dagger A, but the algebra here is not a algebra what we have seen in the earlier case where the operators A and A dagger obeys equal to I. But here the commutator of A and A dagger is not the identity operator. So the Q deformed or the general an F deformed oscillator, you can write it in this fashion. So when Q tends to 1, this is our harmonic oscillator or the electromagnetic radiation algebra we are going to get. So when Q is not equal to 1, it is basically giving you algebra, which is very different than whatever the Lie algebra we have been seen earlier. So in this case, so first thing is, so in the F deformed oscillator, there are different types of F deformations. One is the math type, and other one is the physics type. So we are now looking at a math type Q deformation. So in math type Q deformation, in the earlier page, what we have seen that Q, there is a capital Q. If you set that is equal to Q square, and this bracket n is equal to this one, you get a math type Q deformation. So in this case, the small q value can run from 0 to 1, and so this has been, see, this is actually, there is no so far no experimental verification for this Q deformed oscillator. People have been trying for this, but there are lot of quantum gravity and string theory people actually use this deformation for analyzing their systems. So here we are considering this as a one theoretical model to understand, because there is a nonlinearity in the operator itself, if you want to say, and so you don't have to go for the nonlinear Hamiltonian in the sense of the order of the operators in that. So that we will see shortly. So this Q deformed states have been there in the literature for quite some time, but what we found that the wave functions for this Q deformed states are actually not well described or given in the literature. So we actually using the quadrature operators, we actually derived, we've actually found these wave functions for these Q deformed oscillators, and so that is just I want to add. So here the Hamiltonian we write is this A dagger A. So basically this is A dagger A. You know that A and A dagger obeys this commutation relation. So in this case, what happens? Suppose you take a initial coherent state in this case. So your Hamiltonian is just whatever I have written earlier, A dagger A plus A dagger. So it is, there is no higher order in that, because A dagger square A square term is not there. And state we have written is basically ket alpha. So here you can see that even for mod alpha square 1 and Q, so there is no interaction between the systems. It is a one-dimensional system. So here this is the first return distribution. So first return distribution is basically you take the phase space, you consider a small cell in that, you find out how much time the system takes to come back to that cell, okay, and find out the probability for each of those coming backs. Okay, you find out the time it takes for each coming back to that cell and find out the distribution for that. So that is this F1. So if you calculate this, if it is a periodic, you get 1 or 2 peaks maximum, or you get only 2 peaks. If it is a quasi-periodic, you will get more than 2 peaks. So here you can see that we get only very small peaks, and this is the recurrence plot. So recurrence plot actually is when the two the trajectories are very close to each other, we say that we give a matrix representation for that. Then we put it is 1. If they are very far, we'll put 0. So this will tell you if you have a periodic lines in the diagonal. You can see a diagonal line here, and there are lines parallel to that. Then it is completely a periodic system. But the interesting thing is that when you go to a Q value, so Q value is the deformation parameter. So the Q value, if you change to less than 1, Q tends to 1 is the usual our harmonic oscillator Hamiltonian. So when Q can take values from 0 to 1, and so now you can see that we reduced the Q value from the actual harmonic oscillator. So there is a deformation. So in this case, so there is a Lyapunov exponent coming into this case. So this second plot, which gives lambda versus Q. So in the lambda versus Q, you can see that for Q tends to 1, and this lambda values actually becoming very high, high values, and for less value of Q, there is still, it is a positive. So lambda, the Lyapunov exponent positive means there is a chaos. But when Q tends to 1, at Q equal to 1, you can see that it suddenly dropped to 0. And it is more chaotic near that q equal to 1 value. So this is a very interesting calculation we have performed. So in the case of q deformation, you don't have to go for a nonlinear Hamiltonian in the sense that the operator, and you don't have to go for an interacting system. So here you can actually see this ergodic and chaotic behavior in the system variables. So this you can use the power spectra if you plot. So q equal to 0.999 means that it is very close to the harmonic oscillator case. Obviously, that case it is a periodic thing. So you can see that the spectrum is very peaked here and it does not show any kind of chaotic nature. But when q is equal to 0.90, it is away from that harmonic oscillator thing, non-deformed oscillator. Now we can see that there is a band in the structure. So this is just a qualitative way of saying whatever we said regarding the qualitative measure lambda. So we actually for mod alpha square, that is the mean photon number, and q is the deformation parameter. We have actually plotted this where this system can show periodic orbits, where the system can show quasi-periodic orbits and chaotic orbits. So this range, it shows a chaotic orbit. So that means very large mod alpha square value and very close to q is equal to 1. So that is the result here. So that I have stated here. So this system exhibits periodic behavior between q is equal to 0 and 0.2, and quasi-periodic behavior in the range q is equal to 0.2 into 0.4. So it is basically in the classical system, you can see that there is there are different routes to chaos. So periodic doubling route to chaos, quasi-periodic route to chaos. So here, what we are seeing is there is a quasi-periodic route to chaos. So that is what we find here. And the dynamic here is also explicitly dependent on the deformed coherent state value alpha, and chaotic behavior is observed quantitatively and is qualitatively and quantitatively verified using the Lyapunov exponent. Okay, so we also have seen other reference plot, power spectra, and first return statistics. So all these studies confirms our results in this paper. Okay, so initially I talked about regarding this a system which actually shows periodic thing irrespective of whatever initial state you consider, and then but if you change the superposition, then what we see is that there is a change in the dynamics. So it may be the change may be in terms of the period of the system, or it may be in terms of the dynamics. Maybe it can go from a periodic system to a quasi-periodic system, or it can go from quasi-periodic to chaotic system. So this is what we are observing here. That means you keep the Hamiltonian same, and you take an initial wave packet, you find some dynamics. Then now take the same initial state and make a superposition of that initial state. And then what we find is that the dynamics drastically changes. So certain cases that change may not be drastic, like the case of the Kerr medium, where it actually just change the periodicity. But in certain cases, the dynamics completely goes from a periodic to quasi-periodic, or quasi-periodic to a chaotic or ergodic orbit. So that is the other interesting thing we are observing here. So nonlinear dynamics of superposition of quantum wave packets in systems such as Kerr media and bosonic Josephson junction is studied. So for this purpose, actually, we have carried out this analysis and Morse oscillator, Kerr medium, bosonic Josephson junction. So various quantum systems has been studied in this case, and we find a very interesting transitions when you go from one state to its superpositions. So whatever I said earlier, so the Hamiltonian, so first let us look at the Kerr Hamiltonian, where the Hamiltonian is h cross chi a dagger square a square itself. So this one we have already seen. This Hamiltonian shows a periodic orbit for the dynamical variables in the systems, or expectation values in the system. So now you take, for example, coherent state ket alpha, you take a superposition of coherent states that you can write it like this. So what happens to the dynamics? So you can, this actually, you can see that this is a periodic orbit of the phase space. So average value of P versus X we have plotted in all these cases. For one is P versus X, another one is P square versus X square, and PQ versus S cube. So all these cases, you can see that the phase space picture may get complicated, but the system comes back to the values, comes back to the initial values. So this is basically shows there is a periodicity in the variables. Now, in the previous case, this case, if you increase the, if you change the initial state to that superposition state I have described here, if you change the initial state to the superposition state I described here, then what happens is the period changes. So I am not showing that here because it's not that much interesting result, because this just changes the period of the dynamics. Now you consider the Hamiltonian, which is actually one additional term has been written, which is a dagger cube a cube. So physically may not be that relevant, but this addition, there is a one more term added here, but it is becoming a more nonlinear and higher order. This coupling is there, that is chi prime. Now in this case, so what you can see that, so this is for a coherent state. So initial state is a coherent state. So first return distribution. So first return distribution, whatever I said, you consider a cell and find out the distribution to find out a distribution the time obeys for each return to that particular cell. So if it is an ergodic system, that return should show a exponential decay. So that is what ergodic theory says. If it is a periodic or quasi-periodic, you will see more peaks in that, but it will not show any this exponential decay. So the first plot is for a coherent state, and second one is for a superposition of two coherent states. Basically, we have taken even coherent state. So now you can see that when you go from a coherent state, a superposition of two coherent states, the Hamiltonian given earlier, the system goes from a quasi-periodic orbit to a ergodic orbit. So this is interesting because when you change the initial state to a different superposition, it is showing a different dynamics altogether. So this is same thing in terms of the recurrence plot. So recurrence plot, so this recurrence plot, basically if you have a diagonal line and parallel lines with that, then it can be periodic or quasi-periodic. But if you have a abrupted lines coming into the recurrence plot, it's a well established theory. If you have a one only single diagonal line and there are points in that recurrence plot, then it is a signature of ergodicity or chaos. Okay, so that is what we are seeing there in that particular Hamiltonian. When we go from one state to its superposition, the dynamics can go from quasi-periodic to a chaos or periodicity to quasi-periodicity. So same thing we repeated for the Josephson junction. For that we have considered the BSc, this Bossabard model. Then I'm not getting into the calculations. So we can write down the angular momentum basis this state. Okay, SU2 coherent state, you can write get theta phi in the angular momentum basis. And depending on theta and phi, we have a different kind of states. Now we are looking at theta equal to pi by 2 and phi is equal to pi, is called a pi state. So in this pi state, what happens is, again, you can see that for a pi state, what you get is a quasi-periodic behavior. But when you go from a pi that to an even state, that basically the superposition of two pi states, if you take, then you get a chaotic ergodic orbit. Okay, so this is what basically, so we have done this for various systems, different types of initial states, and whatever our results we have been getting over the years, like periodic orbit, quasi-periodic orbit, chaotic orbit. All these things we can easily analyze using the dynamical variables and its time series. So this is this is what I would like to convey to the in this conference. So now I think I am open to the questions.
Thank you very much, Dr. Sudhi Senthil. Yeah, so now the house is open for questions. So if you have some question, please raise your hand, and then we, or you can also write in the chat box directly. Is there a question? So far, I don't see one. So in case you have question, please raise your hand, or you can write also on the chat box. Okay, so apparently I don't see a question. So in case you have some question later on, you can directly write in this chat box or directly maybe contact to Dr. Sudhi, and I hope he will entertain and answer these questions. So since there is no question, let me thank the speaker once again for this interesting talk and so. So thank you very much, Dr. Sudhi Senthil. Thank you very much.
Yeah.
So
thank you, Dr. Manavendra.
Thank you very much. Yeah. So with this, we are actually at the end of this third session, and I would like to thank all the speakers, all three speakers in this session. And with this, I would like to hand over the program to Professor Arvind, who will be chairing the next session. Professor Arvind.
Manav, I think there's still some time left for this session. So
Okay. So
it will start at 7:30.
7:30. Sorry. Yeah, you are right. So okay, so with this we close the session here. Our next session will start at 7:30 today. Okay, so we'll see you there again. Thank you very much.
हेलो ठीक है हाँ सुन रही हैं
Yeah, hello Arvind. We have said the session will begin at 7:30. I can see David is logged in, so maybe he can, share his slides or something.
Sure. Let me share my screen.
Hi, David.
Hi David, how are you?
Hi, good. Good to talk to you.
Good to see you.
Right. Does that work
And
with the
thanks
slides?
for accepting our invitation.
Oh,
So
yeah,
maybe you
no,
can
it's a
share
great
your
honor.
screen.
Yeah, sure.
David, you have a wonderful office. It looks like an art studio.
No, it looks like a studio. It's
Yeah,
like a studio.
the common reaction of my colleagues is that I should get some furniture. And I agree, but I always defer to tomorrow. I'll get some furniture tomorrow.
But I think it looks great just like this.
Thank you. So here, for example, this painting was done by my father-in-law. It's called The Black Hole, for example. See, there is actually some personalized artwork in here, just not done by me. Let me test one thing. I have a laser pointer. Can you see that? Let's hope. All right. I'll be back in 1 minute.
No, take your time. You have about 5 minutes. See, the talk is about magic, so David is kind of producing sounds to begin with.
All right, so I hope people can hear me. My network is somewhat fragile.
I can hear you fine.
Kavita, can you confirm that I'm audible? All right. So let me begin this session. Before I begin the formal introduction to speakers, let me also mention that while this conference has been going on for the past 4 days, today is the 5th day, the penultimate day, our country is kind of going through a very serious crisis.
So I no longer hear the chairman. Is it just me?
Arvind, you're not audible anymore.
Yeah, am I audible now?
Now you're back. Yeah, crisis was the last word that I heard.
So there is a serious standoff between farmers and our government, and there's a crisis situation. Today, the entire country was standstill because of a large number of public protests and public discussion going on about this. Tomorrow is a very crucial meeting between the farmers and the federal government, and we hope that this crisis end with some positive note. I thought I'll mention this. This conference, of course, is going on because it's an international event. And
again, you dropped just now, Arvind.
Let me begin the session. The first speaker in the session is Professor David Gross. David Gross did his PhD with James Isert and was subsequently a postdoc at Braunschweig and at ET at Zurich. Currently, he is a full professor at University of Cologne. He has been involved with very many different interesting pieces of work in the area of quantum information. And today his title is very interesting. He's going to talk about operational versus axiomatic approach to resource theories of magic. And I can see the room he's talking from looks quite magical, and I hope he will show us some quantum magic. So over to David Gross.
Yeah, thanks, Arvind, for this kind introduction. Thanks to the organizers for putting together that workshop. Yeah, indeed, I chatted a bit before the session started. My room is famously empty, and all my colleagues, they say I should get some furniture, and I always defer it and say I'll get some furniture tomorrow. Also, thanks, Arvind, for telling us a bit about the political situation. I've read a bit of headlines, but only, of course, superficially. What is going on, and I wish that this political woes will calm down and that 2020 doesn't add yet another negative event. In any case, so let me distract you a bit by talking about magic and the resource theory thereof. Everything I'm going to present today is joint work with two PhD students, Arne from the math department and Markus from physics. And Markus also is in the audience, as I've seen before, so he can help me answer questions. Okay, here's the outline. I will give a relatively long introduction to the background, remind you of the Gottesman-Nil theorem and the resource theory of magic. I will then only later in the talk mention our results, and I have some slides prepared about the technical proof. I don't know whether I have time to show them, but anyway, they are in my deck. Okay, so let remind you or tell you, if you were not exposed to it before, of the Gottesman-Nil theorem, a central result in quantum information theory, of course. And the Gottesman-Nil theory considers quantum circuits that are composed of a certain number of components, namely the following primitives you are allowed to use. You can prepare new systems in the computational basis, and you can perform measurements in the computational basis, also of individual systems. And you can apply quantum gates, unitary operations, but not any set of quantum gates, only those chosen from a particular subset. And the subset includes the phase gate, which is shown down here, if you can see it, this diagonal matrix with 1 and I on the main diagonal, the Hadamard gate H down here, control Zs, and gates like that. So if you restrict, you have to restrict your dynamical evolution to these certain subset of gates. Also, you are allowed to use classical randomness and classical control. So which unitary you apply and which measurement you perform, this can all be conditioned on the outcomes of previous measurements. And if you do this, then the Gottesman-Nil theorem states that these operations can be efficiently simulated on a classical computer. And so this is maybe surprising. It is surprising because it's a very rich class of operations. It can create highly entangled states. And so it's by no means obvious how a classical computer can keep track of those, but it can, right? And so many constructions in quantum information theory, in particular in quantum error correction and quantum coding, they rely on these primitives because they are rich enough to show interesting behavior, but well structured enough that we can keep classically track of them. So let me, in one slide, just sketch how this works. So the reason that these circuits can be simulated efficiently because in such a circuit, at any time, the state may be represented as a pure stabilizer state. And the stabilizer state, in turn, is a state that can be described via its stabilizer group. And I don't want to give the general definition, but instead I give you one example. So let's say you want to talk about this maximally entangled state, 0, 0 plus 1, 1. Then it has two invariances. Yeah, if you flip both bits, if you apply the sigma x tensor sigma x operator, then you turn all the ones into zeros and all the zeros into ones, and then the state remains the same. And if you apply the sigma z operators to each of the qubits, then the first qubit will not change because you get a +1. And the second one will also, the second term here will also not change because you get a -1 twice. So again, everything stays the same. So the state shows these two invariances, and in fact, it is the unique state to do so. There's only one vector in Hilbert space that is invariant under these two operators. So I might as well characterize the state not by writing down the expansion on the computational basis, but by giving its stabilizers, its invariance group. And for this particular state, it seems like there is no need because 0, 0 plus 1, 1 is easy to write down. But if I look at a general n-qubit stabilizer state, then it's going to be very difficult to write it down in the computational basis. You need 2 to the n terms, but the stabilizer group always gives you a compact, a concise characterization using the order of n squared bits, where n is the number of qubits involved. Yeah, and so this is how the Gottesman-Nil theorem works, by keeping track of this description. Okay, so let's go. This is all known since the 1990s. Let me tell you a bit about more recent developments beyond Gottesman-Nil. Right. So the first notion is now the notion of magic that I will introduce here, but not yet quantify. This comes a few slides later. So it is known that if you break this restricted class that I introduced before by introducing a supply of any non-stabilizer state, then you can perform universal quantum computation. So you go from classically simulable to universal immediately. Yeah, and for example, the state down here is not a stabilizer state. And yeah, it's called the H state. And if you have it, for example, you can perform arbitrary computations. And the proof that this is true goes via what is called a gate teleportation gadget. So if you have an unknown input state psi, then you can consume one of these magic states H and do a teleportation circuit, and the teleportation circuit will result in a non-Clifford gate acting on your input. Yeah, so with this magic state as inputs, you can simulate non-Clifford gates. Right, and since non-stabilizer states, they contain the secret sauce, yeah, that makes blend circuits universal. They are called magic states because they apparently contain all the magic of a quantum computation. Right, this can be generalized even further to certain mixed states. So if you have certain mixed states, then you can take many copies of those and use a procedure called magic state distillation to reach a pure magic state, which you can then use for universal quantum computation. So this means magic is sometimes also contained in mixed state. Okay, so let's go in a different direction beyond Gottesmann-Hill, in the opposite direction, and don't talk about what makes a circuit universal, but what other things can be simulated. And for this, we define a central notion. It's called the stabilizer polytope. And the stabilizer polytope is the convex hull of all stabilizer projections. What you see here is the Bloch sphere and this double pyramid. This is the stabilizer polytope with the eigenstates of the sigma operators at its vertices. And if the state of your system is in a mixed state, which is contained in the stabilizer polytope, then this immediately suggests an efficient Monte Carlo simulation algorithm for the circuit. Namely, you just decompose your state that is contained in this pyramid as a convex combination of these extremal stabilizer states. Yeah, and then you reinterpret the convex combination as a probabilistic mixture. You toss a coin with outcome probability proportional to the weights, and then depending on the outcome, you continue the simulation with the extremal stabilizer state that corresponds to the outcome. Yeah, and this has been known for quite some time that this is possible. And in some cases, this way you get a tight characterization between magic and Monte Carlo. Yeah, so here's a cut on the right-hand side to the Bloch sphere. Everything inside this square is simulable in this Monte Carlo way, so it's boring. But as soon as you go outside, then you have universal quantum computation. So in some cases, we can neatly divide state space into simple and magical states. All right. There's recently even more generalizations to all this, but I don't really want to talk about this. Just for completeness, I list them for QDITs, not qubits, but higher dimensional system and continuous variable system. You can have other classical simulation results via non-negative Wigner functions. Recently, people got very interested in coherent superpositions of a few stabilizer states as a boring resource that can be simulated classically. It's very exciting, the theory, but I don't want to talk about it today. And very recently, the group by Robert Rausendorf and friends, they've been looking at an even more geometrically advanced theory. I just put a figure here, that kind of symbolizes that the math they do is non-trivial. But again, I don't have, for the reason I don't want to get into any details. Good. So now we know about Gottesmann-Hill, and we know that stabilizer states and Clifford operations are simulable, and that sometimes there is magic that you can add that makes this setup universal. Let's try to quantify magic and build a resource theory of magic, where, well, I've said it, where we want to quantify how much magic there is in a given system. All right, and so to do this, let's again look at the stabilizer polytope and be a bit more concrete. So a density matrix, rho, is an element of the stabilizer polytope if and only if I can decompose it into this convex sum, where the Si are stabilizer states and Pi, these form a probability distribution. Yeah, if rho is not in the stabilizer polytope, then I can still expand it in terms of stabilizer projections, but now the coefficients, they might sometimes be negative. Yeah, it's no longer a convex combination, but an affine combination. And now maybe if you have an education from quantum many-body physics outside of quantum information, it has long been known that the technique called quantum Monte Carlo can deal with non-positive signs. Yeah, there is a technical way of doing it. I don't want to explain the algorithm here. Basically, you take these expansion coefficients and you take their absolute value and you renormalize them so that you get a formal probability distribution out. But now you have to worry about the signs extra. And then what this Monte Carlo algorithm does is it simulates every experiment many, many times. And one can show that in the limit of many, many runs, on average, it gives you the right result. And but in general, you have to take many averages and many runs in order to get the statistics right, a phenomenon that is known as the sign problem in quantum many-body theory. Yeah, and so you can now ask a bit more quantitatively, what is the overhead in quantum Monte Carlo? How often do I have to run the algorithm so that I get the right result? And one way of measuring it is using the robustness of magic. Yeah, so you take your input state rho, you expand it in stabilizer projection operators, and then you sum up the absolute value of the expansion coefficients and you take the logarithm. If it's a convex combination, then the sum of these expansion coefficients is 1, so the logarithm is 0, but in general, it's bigger than this. And the value you get here can be linked to the computational complexity of simulating this problem via quantum Monte Carlo. Okay, so now we have a complexity measure of magic. There's actually many different like small variations of these algorithms, and every variation gives rise to a different complexity measure, but one that is studied particularly well is this robustness measure. So we can now say precisely what we mean by how much magic is in a state. Okay, and now if you've studied resource theories, you will have come across, you will have been exposed to the fact that there is an important question associated with every resource theory, namely, which operations should be considered free in a resource theory of magic? So what should be the operations that do not increase the robustness, or that should not increase any complexity measure of magic? And before we try to answer this question, let's look at other resource theories that are better known and maybe they can guide our intuition. So let's look first at entanglement theory. Okay, so in entanglement theory, there are two well-known approaches for how to get, how to define free operations. The first one is the operational approach. Operational here means in terms of things you can do. Yeah, and there one commonly demands that entanglement measures, so entanglement measures, of course, are the analog of our robustness measures, so quantitative measures that measure the non-locality of a state, that entanglement measures one demands be invariant under local operations and classical communication, right? So that is what the free resource is, or the free operation is in entanglement theory. However, there is a different approach that is equally valid, and that is what I want to call the axiomatic approach. Namely, one can say a quantum channel should be free in a resource theory of entanglement if it maps separable states to separable states. Yeah? And this is now axiomatic as opposed to operational, because in general, it's not clear if you give me one of these channels, it's not clear how I would actually implement it. Yeah? But it has certainly a good claim to being called free. So now, obviously, the obvious question is, do these two approaches coincide? And thing is, and it's known since the 1990s, one of the early results in quantum information is that local operations and classical communication, the operational class, and SEP, the class of separable or separability preserving channels, they do not coincide. So there are some separable channels that cannot be implemented using LOCC. Yeah, here's maybe like a way of gaining intuition about this. I'm not sure whether one can turn this into proof. I've never tried, but here's why this is maybe plausible, that SEP is bigger than LOCC. So here, what I wrote down on the left is an LOCC channel. What I mean by this, you have two inputs, a qubit above, a qubit below, and you perform a measurement, let's say a non-demolition measurement, where I perform a measurement, I get a classical outcome, which is the dotted line, but I also retain the quantum system. And then conditioned on my outcome, I perform a unitary on both lines. Yeah, this is something that I can do, and certainly it only uses local operations and classical communication. But now I can consider the time reversed operation, where the unitary is controlled not on some event in the past, but on some event in the future. Yeah, mathematically, I can easily write down the POVM elements corresponding to this. Basically, I just transpose all the old Gauss operators. But of course, it's completely unclear whether I can actually implement it. Certainly, I can't implement it as sketched there because retrocausality can't be done. You can't condition what you do today on the outcome you will obtain tomorrow. Now, this is not quite a proof that the two classes are distinct, because it could be that there is some different way of realizing this time reversed channel that is actually causal. Yeah, this is not easy to see whether this is the case. But these examples, they should tell you that you should maybe expect these classes to be different. All right, so now we come back to resource theories of magic, and come back to our question. What should be the free operations in this case? And this is a question that has been raised relatively recently by Earl Campbell and James Seddon in a paper that appeared last year. And okay, so first they redefine and reaffirm the operational approach. And the operational free operations, these are the stabilizer operations that I listed in the beginning of my talk. So, add in fresh systems in the computational basis, apply Clifford unitaries, these Hadamard's phase gates, C-knots, and measure in the computation basis. Yeah, all these primitives, these are called stabilizer operations. But equally, there can be now an axiomatic approach, and that is what they defined in their paper. And so they define the completely stabilizer preserving operations as those operations, those quantum channels that preserve the stabilizer polytope. So those quantum operations that map convex combinations of stabilizer states to convex combinations of stabilizer states. And now the obvious question is, are these the same? And the result is, yeah, you wish, of course. Whenever, things could be easy in quantum information, or they could be a bit more complicated, they turn out to be a bit more complicated. And that is the result that I want to present here, of this paper. Okay, so we say, so our result is that as in entanglement theory, the two approaches do not coincide. Right. I will now give you the outlook, and then I'm done with what I want to tell you, and then however much time I have, I will devote to telling you a bit about the proof. Okay, so what we have proved is this: it's stabilizer operations. It's a subset of, but it's not the same as completely stabilizer preserving operations. And there are two consequences. If you are a theoretician, then you are happy, because it means the structure theory is more interesting. Yeah, there are two different things to be distinguished. But more practically, it means you have another class of operation that can be efficiently simulated beyond Gottesman-Nil. Yeah, for this efficient simulation algorithm, it is well, almost enough to have a convex combination. So it means there is more a classical computer can do, trying to catch up with a quantum computer. I have to warn you that the details are not really worked out yet. There is some work done by James Seddon in this paper in 2020. But but just having a convex combination is not enough for an efficient simulation algorithm. You also have to have some way, for example, of sampling from the different summons in the convex decomposition. You have to sample from those efficiently, and that is not always obvious how you do it. It's very plausible that there will be big new classes of simulable processes, but I think it's a very interesting problem to have to see the details worked out. For example, by you in the audience. So that's why I'm presenting that here, a bit also to kindle interest in this research program. Okay, so now you know the background of why we looked at this question. You know what the result is. And I have, 15 minutes. So I will talk a bit about the technical details. Let's see how far we get. Okay, so let me tell you first a bit about the structure of completely stabilizer preserving operations. And the first thing that is surprising maybe is that any operation that maps stabilizer states to convex combination of stabilizer states is in fact completely positive. That is surprising because complete positivity is a very strong property. And in what I just said, I didn't, obviously imply it. But the proof is also very simple. Yeah, if you know your Choi-Jamiukowski theorem, then you know that complete positivity is equivalent to demanding that the image under the channel of the maximally entangled state is a density operator, is positive semi-definite. But the maximally entangled state is a stabilizer state, or if you want to talk basis independently, can be chosen to be a stabilizer state. So stabilizer preserving means also the maximally entangled state will be mapped to a convex combination of stabilizer states and thus a density operator. Speaking of Choi-Jamiukowski, here's a stabilizer version of Choi-Jamiukowski. As you remember, again, Choi-Jamiukowski establishes this 1-1 correspondence between dynamics and states. Yeah, that's again surprising because states seem to be much simpler than dynamics, but they are the same by this isomorphism. And this is, there can be a stabilizer version, which goes back to James and Earl's paper. And they show basically that the Choi-Jamiukowski image of the set of completely stabilizer preserving operations is just the stabilizer polytope in a doubled space. Yeah, so if you take all the stabilizer states on 2 n qubits, take their convex hull, this exactly is the Choi-Jamiukowski image of the completely stabilizer preserving operations on n qubits. Yeah, so simple structure can easily be established. All right, now I come to our counterexample. It's the channel that is completely stabilizer preserving, but cannot be realized as a stabilizer operation. So it's this channel lambda, which, the mathematical definition is up here, but nobody can understand that so quickly. So let me describe to you in words what that thing does. So first, you get some input, some n-qubit state. And the first thing you do is you apply a dephasing operation where you reduce all off-diagonal entries by a factor of 1/2. Yeah, so that's the 1/2 here. Yeah? So all off-diagonal elements get attenuated. Then you perform a projective measurement where you look, is the state, am I in the state, everything is 0, all qubits are in the 0 state, or somewhere orthogonal to it. And if the answer is 0, 0, 0, then conditioned on that event, you apply a Hadamard gate to every qubit. Yeah. So this you can see here, rho 0, 0, 0 is the coefficient of the all 0 ket, and this gets turned into the plus state. So the Hadamard has acted here. The main diagonal remains unchanged, and the off diagonal gets attenuated. Now this looks like a weird combination of things. I mean, how does anybody get the idea of combining 1 with 2 with 3? And well, it took us a very long time to find out, or more precisely, took Arne a very long time to find that out. He came up with this counterexample, and let me try to give you a feeling for why he had the feeling that he had to go down this complicated path. All right, so here's the claim about lambda. First, lambda is completely stabilizer preserving. That is not obvious, in case you wondered. It is, moreover, an extreme point in the convex set of CSP operations. This is extremely non-obvious and takes a very long time to prove, and is the main technical difficulty of our result. And lastly, it is not a stabilizer operation, also not obvious. So what I want to do in the last, I don't know how many minutes I have, few minutes, is I want to talk about the third point. How can we see that it's not a stabilizer operation? Because I think there's the most, content I can get across, in the remaining minutes. And I wanted to say, why did we have this complicated state? Mainly to ensure extremality. So all these coefficients here are fine-tuned so that we get something extremal out. Okay, right. So now about that. Okay, how can we show that a channel is not a stabilizer operation? And first, let's look at a simple example. This is an extremely simple stabilizer operation. It's just a measurement in the Pauli Z eigenbasis, a measurement in the computational basis. So clearly, if the channel is just a measurement in the computational basis, it is invariant under sigma Z operations. So whether I directly measure or first apply sigma Z and then measure, that's obviously the same. And the proof strategy is now as follows. We want to show that stabilizer operations always have some kind of Pauli invariance, as I just depicted above. And then we show that our counterexample doesn't have the stabilizer invariance. And then we know it can't belong to the stabilizer operation set. So now we got within the team, we got into like a bit of a back and forth, where now there is always one person who makes an unfounded and completely overconfident and overgeneral statement. And then if you hear that person speaking, you can think of me. And then there is here retort by better informed and more careful researchers who say, yeah, it might not be as easy as you think. And if you hear that, you can think of Marcus and Arne. So I say, well, obviously all stabilizer operations have a Pauli invariance. And then I hear, well, not if they are Clifford unitaries. If they are Clifford unitaries, they are stabilizer operation, but there is no measurement. And then I say, oops. Okay, obviously, all except for those, clearly that's what I meant. And then they say, but what if you throw a coin and then decide which Pauli to measure? Then depending on the outcome of the coin, you have a different Pauli invariance, but after you mix, you don't have an invariance anymore. And then I say, okay, obviously, only the extremal ones that aren't Cliffords. Clearly, I meant that. And then they say, but what if we entangle the input with an ancilla prior to measurement? Yeah, okay, fine. Now they had me, and now we spent another 2 weeks looking at this case. So let me tell you about this case, and that's almost the final ingredient here, right? So, so basically the next case we have to handle is a stabilizer operation of this form, where you have an input in some unknown state psi and an ancilla input, and you entangle them, and then you perform a measurement on one of them. And that is your output. Yeah, that's certainly a stabilizer operation. Now there are different cases. There is the case that, for example, U is actually a tensor product, so that I measure only on the ancilla. Then I don't need to measure at all, so I can easily handle this case. Or there is the case where the unitary is a flip operator, and I just have a measurement on the input. That's exactly what I want. I want a measurement on the input so that I get an invariance. But then there is the more difficult case that there is a true entangling operation, and I just measure half of the output. And then one can see, though, that in the latter case, one can always find a convex decomposition of that channel into two other channels that just apply a unitary. Yeah, and if I restrict myself to extremal channels, I can only look at one of these two summons, and then I'm back to a unitary, the case I've already treated. And in one word, why does this work? It's basically the quantum error correction condition. So what's happening here basically is that what we're doing here, having a stabilizer ancilla and then encoding using an entangling unitary, that brings me into a stabilizer code. And if I do a local measurement on a stabilizer code, then I can recover the input. So that's basically what is behind that. But if that was too fast, never mind. I mean, it's in the paper. And okay, I claimed that I always totally knew this, but of course that's a lie. I just, had I made the right conjecture by chance, and it turned out to be correct, even though I had no reason, in retrospect to know that. Okay, so if we combine all these, all this back and forth, then we get a theorem, and it says that every stabilizer operation that is extremal has either a Pauli invariance, that's case 1, or is basically a Clifford, that is case 2. Yeah, it's stated here a bit differently because, for example, we also want to handle a stabilizer operation that go from few to many qubits, but that should not concern us today. Right, yeah, but then we're done. Okay, now we have shown that, let me go back to the proof strategy. Yeah, we have shown that not every stabilizer operation has a Pauli invariance, but every extremal one. And then we show that our counterexample is extremal, but it doesn't have a Pauli invariance. And so hence, in this very indirect way, we have shown that there are things that preserve stabilizerness, so that can be efficiently simulated in a Monte Carlo algorithm, even though they are more general than a combination of stabilizer and Gottesman-Nil primitives. So that means that we can simulate more than we thought we could simulate. Yep, and that's all I wanted to say. So thank you.
Well, thanks, David. So now the house is open for discussion. If you have a question, please raise your hand in the raise hand box. I already see Gaurav Saxena has raised his hand. So Gaurav, you can unmute yourself and go ahead.
Sure. Thank you, Professor Arun. Hi, David. Can you hear me?
Hi, yeah, I can hear you well.
Yeah, so I have two quick questions. The first question is that when you said that these completely stabilizer preserving operations can be represented as stabilizer states in a double space, I want to ask whether all these states in this double space correspond to completely stabilizer preserving operations?
Yeah, it's if and only if. Yeah,
I see.
You refer to this. There's like one tiny caveat, but basically, yes, here, you refer to the stabilizer Choi-Jamiukowski. So let me just, to get a better feeling what we are comparing it with, let's look at the normal Choi-Jamiukowski. And that says, if you take the completely positive trace-preserving operations, then under Choi-Jamiukowski, that maps exactly to the positive semi-definite states on a doubled or operators on a double space. Plus, there's one extra condition that corresponds to trace preservingness. Yeah, and we have this the very same statement here for the very same statement we have here. So we get all right. So if I look at the symbols here, completely stabilizer preserving maps.
Yeah. Are
now,
there any other questions?
Sorry?
Yeah.
Vikesh, please go ahead.
Okay. Maybe I finish the sentence because I think there's like a.
Vikesh, please unmute yourself and go ahead.
Yeah. Okay. I think there's a delay in the line. I wanted to like have half a sentence as left. Like let me just look at these symbols here, right? So CSP, these are the operations. Yeah. J is the Choi-Jamiukowski isomorphism, and you get exactly the doubled stabilizer states intersected with this trace preserving this condition. So yeah, there's a 1-1 correspondence. Right. Okay. So that was my answer, and I think now the next one in line, Vikesh wanted to ask a question.
Hi, David. Can you hear me? This is Vikesh here.
Yeah.
I had a question, which was, you have these magic state distillation protocols. How does one benchmark them against sort of the best possible protocol that could have been constructed?
Okay. Wow. Right. Okay. So a bunch of answers. So one, I'm not sure I know the answer. B, I'm not sure the answer is known, right? And so what you want to say is like in communication theory, you have two dual approaches. You have like particular codes that achieve certain rates, and you have entropic upper bounds on rates, and sometimes they get very close, and then you have it when they meet. Yeah. So for magic state distillation, we have a similar scenario. You can come up with magic state distillation schemes, which incidentally use a lot of coding theory, so that is related. And then you also have converse bounds. For example, you have these monotones, for example, the robustness that I mentioned here, right? And so monotones, as I said before, they are invariant under the free operations, and the distillation is composed of free operations. So sometimes you can make these upper and lower bounds meet. Sometimes you can give a robustness-based, upper bound to how good you can distill, and you can actually write down an algorithm that achieves it, and then, like in coding theory, you are done. But we have not achieved this as a field in general. So there are states for which one can, write down certain distillation schemes, and one can write down upper bounds, but they don't match. Yeah. So sometimes the answer is we don't know yet.
Okay, but the upper bounds are known to be sort of tight in general in some asymptotic sense, or is this upper bound and upper bound?
Yeah, I don't think this is known. There is so this, yeah, there is a lot of work that went into this. And for example, if you look at this block sphere pyramid, then I don't know what the concrete state is. I think for everything in the equatorial plane, I think it is known to either be distillable or simulable, but there are even regions, I think, above this phase where we don't have an algorithm that simulates these things, but also we don't have a distillation protocol. So in general, it's not as good as Shannon. It's not yet tight.
Okay. Thank you. Thank you.
Sure.
next is Usha Devi. Please go ahead.
Thank you. So I just want to, I'm not sure if I have understood it properly, but I thought if I take S and SP operations, so I have some canonical structures maybe to prove that I don't get the same results. That is, S leads to some canonical structure and SP would have another canonical structure which would not be reached by one another. They are independent. Something of that sort would have proved that S and SP are not going to give us the same results. That is, preserve the kind of Pareto preserving operations and the pure stabilizing operations. So as free operations in resource theory, they are going to give you different results. In order to prove that, I might have taken a simple example, counter example, and arrived at a canonical structure. Am I going in a right direction?
But I think you are going in the right direction. I think this is essentially what we also tried. And of course, now one has to make it precise. And our way of making it precise was exactly this property. So I think the difference from what you sketched and what we did in the end, that you are talking about properties of the end result. But I don't think I know any like property of the output. But I know some properties of the operations that are invariant and that hold for every stabilizer operation. Yeah, I mean, modulo this externality and stuff that I outlined, right? And this is this Pauli invariance. So I think we essentially followed the outline of your proof, with the only difference being that we didn't look at the output of the operation, but we looked at the operations themselves.
Yeah, okay.
But by the way, I'm in no way convinced.
Some simple examples which would show it, and then there is no need for going for the other structures.
I completely agree with you. I'm absolutely not convinced that our proof is minimal. You know, it's actually very long and yeah, I would like this to be cut down a lot, actually. Yeah, there was some discussion in the team where I wanted it to be cut down, but I didn't want to do it myself. And the team also, yeah, they didn't care so much. And they said I should do it myself. So it hasn't happened. So, but I agree with you, you know, it's kind of indirect what we're doing, and it's the best we could do, but it should, I'd be happy if there were a simpler answer. Yeah, for sure.
Thank you very much.
All right, so there are no more questions. Let's thank
I'm
David
sorry.
for
Hey, Professor Irwin, I have one more question.
As usual. All right, please go ahead. I didn't see your hand.
Okay. So, hi, David. I'm sorry, I have one more question. So can you go back to your slide on the invariance property of stabilizer operations where you put it as a conversation between two people? Yeah, exactly here. So here, the second statement where you say that not if they are Clifford unitaries, but Clifford unitaries actually preserve the Pauli group.
Yeah.
Then, I mean, I got confused here because when you said that.
I understand. I think I understand where your confusion comes from. This is a fine difference, right? So Clifford operations, they map Paulis to Paulis, but a measurement has a stronger invariance property in that, you know, it doesn't matter whether before I do the channel, I dephase in the eigenbasis of the measurement. So I can, yeah, so making the measurement directly or making the measurement in the Z basis after applying a sigma Z is the same. So this is technically what I mean here by a Pauli invariance, which is a stronger property than just a property that Paulis will be mapped to multiple of Paulis, which is what the Clifford group does.
I see. Okay.
Yeah.
Perfect. Thanks.
All right. I think more discussion between the two of you can happen in chat box and offline. So let's thank the speaker for a very interesting talk. And now we move on to the next talk of this session, which is by Rishabh. Rishabh is currently at the University of Calgary doing his PhD. He was a student at Aizer Mohali, did his BSMS just this year. I think, if I'm not wrong, he is the youngest speaker in the conference. So Rishabh is going to talk about entanglement versus squeezing, a better way to store non-classicality in a dissipative environment. So over to Rishabh.
Okay, thank you, sir. So,
Rishabh, you have to share your screen.
Yeah, I have shared my screen. So can you see the screen?
So we can see your screen, but we can't see you. So switch on your camera also.
The camera is also on.
All right, no problem. So we are fine. I think you can go ahead.
Yeah, just. So my name is Rick, and today I'll be talking on about entanglement squeezing, a better to store classicality in a dissipative environment. So as we go on, it will become more clear what exactly I mean. So in collaboration with Chandan Kumar, Keetu Narang, and Professor Arvind. So, okay. So first of all, I will talk about some basics of CV system, which we would need. So it's just, I will introduce as most of the people in the field works with discrete systems. So I will introduce the language I'll use in the talk. Then I will introduce the problem, what exactly is the problem addressing in this work. And then we will talk about two different case of baths. One is local baths and another case of global baths. So, okay. So the CV system which we will focus on is a two-mode continuous variable quadrant system. So it will be described by four quadrature operators, Q1, P1, Q2, P2. So these are essentially can be thought of as position and momentum. So these could be described in a better using the vector, which are vectors, and the canonical commutation relations can be expressed in a much easier way using this vector. So here omega is just a 2 cross 2 matrix. We call it a symplectic form. So it's 0, 0, 1, minus 1. Okay. And the annihilation and creation operators could be defined as this. So okay. Now I will describe two basic operations which we will need later on. So first is a single mode squeezing operation. So a single mode squeezing operation could be described as a 2 cross 2 matrix, and this since the single mode, so it will act only on a two-dimensional vector on Q and a beam splitter operation is a two-mode operation, so it would act on a 4 cross 4. It is a 4 cross 4 matrix, and it acts on a four-dimensional quadrature vector, which I just show you on the last slide. So we will be talking about Gaussian states. So what is the Gaussian state? The Gaussian state are the states which have Gaussian wave function distribution in phase space. And the good thing about these states is that these can be described completely by the mean values and covariance of quadrature operators. So this is essentially because Gaussian can be described mean value and its variances. So we will consider zero-centered state, and this is without any loss of generality. The reason is that you can shift your Gaussian states throughout phase space by just displacing them without changing their entanglement contents. And we are actually interested in entanglement content, so we are not concerned about their mean value. So we centered state, that is the mean value is 0. So the covariance matrix. So covariance matrix is a matrix whose elements describe different covariances between quadrature operators. So it is described in this fashion, where delta xi is just this, and the curly brackets denote anti-commutator. So the covariance matrix for calculate using this formula, it comes out to be something like this. So now I will talk about separability criteria assignment. So separability criteria gives a necessary and sufficient condition for separability of any two-mode Gaussian states. And this criteria is mathematically can be stated as follows. And here, if you see A, B, and C are nothing 2 cross 2 matrices. And if you write your covariance matrix in 2 cross 2 matrix block form, then these A, B, C are related to covariance matrix in this fashion. Then logarithmic negativity. So the most basic and important entanglement measure which we use in continuous variable system is entanglement negativity, and it is defined as a maximum of 0 or the logarithm of something called symplectic eigenvalue of partially transposed covariance matrix. So this symplectic eigenvalue could be calculated using this formula, the summation of determinant A plus determinant B minus 2 times determinant C, and these A, B, C are the same matrix here. Okay, now introduction to the problem. So squeezing and entanglement are important signatures of non-classicality in the state in the CV system, and these concepts are different, but there is some connection between them. So you can somehow convert mode squeezing and entanglement, particularly in the context of Gaussian using passive optics. So for example, if you start with the two mode squeeze state, separable squeeze state, you pass through the beam splitter. These two beam splitter, the resulting state is an entanglement. So some sort of conversion has taken place from element. So okay, one second. So people are saying that there is some disruption. So I'll just close my camera. Okay. With this simple beam splitter operation, you can convert some amount of squeezing into entanglement. So now this leads to an important question, because entanglement and squeezing are both important resources, and if they could be somehow interconverted among each other, and we know that the biggest problem in quantum information processing task is T-coherence. Your system is continuously interacting with the environment, and because of that interaction with the environment, what happens is your resources die out. So if one of these resources, squeezing and entanglement, is more sensitive or less sensitive towards the environment, then we can use that in place of another to store resource, and whenever we need, we can convert into that. So that is the basic motivation of this work, that which one of these is more sensitive towards environmental interactions, and could it be used for improving our quantum information processing tasks. So again, we are just considering two-mode system interacting with a thermal device. Hamiltonian of this would be of three parts: a system Hamiltonian, a path Hamiltonian, and a interaction between system and path. And we will discuss two different cases. So what are these cases? I'll just tell you. These cases would be are designed in system to see. So one case would be entanglement interacting with the path, and another case would be squeezing interacting with the path. So resource stored as a squeeze state interacting with the path. We'll see which is more sensitive and so on. So okay, so the case one is, so in all these cases we start with vacuum states. So both the modes are in vacuum state, and then we squeeze them. So we squeeze the first mode by a squeezer by an amount R, and another mode by an amount minus R. So now you squeeze these two things. So the covariance matrix would look like something like this. Now what you have done is you have prepared two mode separable squeeze states. So your resources are purely squeeze state and no entanglement, and you let them interact with the path. And once it has interacted with the path, you mix them using 50-50 beam splitter. So you try to create entanglement by yourself by letting them mix through beam splitter. Whereas in the second case, we start again with two mode separable squeeze states, but now instead of letting it interact with the path and wait to use the beam splitter to mix them, we entangle the beam splitter initially. And once it has entangled, then the covariance matrix looks like this. And then we let this system. So in one case, we delay the beam splitter operation so that the thing which is interacting with the bath is a resource stored in squeeze state, whereas in the other case, what is interacting with the bath is the resource stored in entangled state. Okay, so so this is essentially said. So case one is a resourcing form of squeezing. In case two, we have converted some squeezing into entanglement using beam splitter operation, and so we exploit this fact that now to answer the main question, that is which form of non-locality, whether squeezing or entanglement, is more resilient to dissipative environment. So, and we consider in this study two kinds of environment. One is when both modes interact with a single global path, and the second environment we consider is these two modes interacting with the individual local paths. And we see that in these individual cases, is there any difference between which of these two is more robust and so on. So let's start with the case of local path. So we have a two-mode system interacting with local path, and Hamiltonian the interaction part I've just shown, because the system and the path part remains same in both the cases, so it doesn't matter. So these A1 and A2s are the annihilation operators for the modes, and the B's and C's are the annihilation operators for the respective paths. So you can see that the system is interacting with their individual paths. So this is local thermal path. We assume the Markovian evolution. We use so this for a density matrix rho, this looks like this. So if you know how mean values variances involved, because you can calculate those things using your rho. So if you know how covariances evolve, you can calculate the time evolution of covariance matrix. So essentially using this equation, you can calculate the time evolution of covariance matrix. So now understand these two scenarios. So it's the case of local path, and it's the case one. So in this, what we are doing is we are delaying the entangling operation. So we start with vacuum states in both modes. We squeeze them in R, and with R and minus R as the squeezing parameter. And then we let these two modes interact with their individual thermal paths. And after that interaction with the path, we entangle them. So there may be some entanglement generated by bath, but we are not talking. We are talking about the intentional generation of entanglement by applying the beam splitter operation. And so this is the V1LT is the covariance matrix, which I will show, which you get after all this happens. So the covariance matrix after interacting with the bath for time t. So once you have initial system with the bath, then the covariance matrix is this form, where x and y are given like. Okay, so this is some complicated form. Okay, this. Now, and then you apply a 50-50 beam splitter, and the final covariance matrix is of this form. So, okay. Now the case two, what happens is that instead of delaying this entangling operation, we do this entangling operation initially before letting our system interact with the local thermal paths. So in this case, what is happening is that we have converted some squeezing into entanglement. So we have stored some of non-classicality as entanglement, and now we are letting our system to interact with the path. And the final covariance matrix looks like this, where x and y are again given by these equations. Okay. Now, what are our results for local bath scenario? So we, in local bath scenario, we consider two extreme cases. One is symmetric case. Your baths are identical, and your interaction strength with those baths of your modes is also identical. So this leads, when you calculate, so this leads to the same final covariance matrix for both case. So that means that either you do the entangling operation prior to interaction with the bath or after the interaction with the bath, it doesn't matter, because the covariance matrix which you get is identical. So it doesn't matter in this case. So you can sort of store non-classicality in any one of these, it doesn't matter. Then okay, so the other case, the other extreme case which we consider is an extreme asymmetric interaction. That is, there is only one bath, sort of. So only one mode is interacting with bath and there is no other bath. So in this case, we find some interesting scenario. So depending upon the initial squeezing parameter R, the two mode separable squeeze state, that is the state which you get. So when you have entanglement prior to the interaction with the bath, so your state never becomes disentangled. If your initial squeezing is greater than this value of R, so we call this R critical. And for all the values of R less than or equal to RC, your entanglement dies out, and the time at which it dies out is calculated to be this. So now the time for disentanglement of TMSP state, that is when you interact before the paths. So the beam splitter operation is done before the path, then this comes out with this. And so in case of TMSP, there is always entanglement death in this scenario where there is only one local path. Whereas for the other case, there is entanglement death only if the R is above some critical value RC. Okay, so now which of these is better? So we would we answered this question in this way, that we said the one which is better, for which the entanglement, the amount of entanglement dies out much after than the. So we compare the time of the entanglement death. So if in one case the entanglement death occurs earlier, then we would say that's a bad type of resource to store non-classicality. So so we just compare these two times, tau A and tau B, and we find out that there is a sort of phase transition type thing happening. So above a particular R value, the storing in squeeze state, saving resources in squeeze state is better, and and in the other side, it's the entanglement. So so we have so this plot will help you to understand this in a better way. So you see, so these are plotted for n equal to 4. So for initial values of squeezing parameter, which is R less than this RL, which is that phase sort of thing. So in that case, you see that if you are, it is less than the separable state, that is where you do not do the entangling operation prior to interaction, so it dies earlier, so it's not a better resource in that case. But if you increase the initial squeezing to that critical value, then you will see that that the TMSP case, that is the case in which you do the entangling operation prior to the path. So that is in the case in which you store your resource form, that dies out. So depending upon the initial squeezing, the different, it would be better to store in one in either in squeezing or entanglement. So the answer depends upon the initial squeezing. Okay, so now I will talk about the global bath scenario. So two-mode system interacts with a global thermal bath, and the Hamiltonian interaction Hamiltonian is of this form. So now you can see that both both the modes are interacting with the same path. So B is the B dagger and B are the creation and annihilation operator of the path modes. So again, we are using Markovian master equation for the evolution. Now, since the nature of path is different, so the equation is also different. Again, same that this equation could be used to evolution of the covariance. So, okay, the case one. So, case one is essentially the same, that we are not storing our resources in form of entanglement. The resource is still in form of squeezing. We have delayed the entangling operation after the interaction with the thermal path. Whereas in case two, we will see that we would store the resource in form of entanglement, and this beam splitter operation would be done prior to the interaction with the path. So in the case one, where resource squeezing form, so the final clearance matrix after all interaction and passing through beam splitter is of this form, where these sigmas are like these. Okay. Now, okay. So now the case two is we are converting some squeezing into entanglement. So now some part of resources stored in entanglement, we are letting our system to interact with a thermal path. Now the final covariance matrix in this case is of this form, and these deltas are like this. Now for two more squeeze state, so that is the squeeze state where so two modes and the entanglement is performed prior to the path. So you stored some of your state resource in entanglement form. So there is a critical value of R. So if your R is above, so initial squeezing above this critical value, then entanglement death never occurs. But if it is less than this, so entanglement occurs. So if you remember the case of the local path, only one local path, extreme asymmetric interaction path, it was opposite. For the stable states where you entangling operation stored in completely in squeezed form, classically stored in squeezed form, then in that case the entangled value, whereas for TMSP state, the entangled that did not depend upon any, it never occurred. So what, irrespective of the initial value of R. So now in the, so two mode separable squeeze state, that is where you have delayed the entanglement. Now the entanglement, so the entanglement that always occurs at the time of this entanglement. This is given by this. Okay. Now, okay. Now, in the same, similar to the local path scenario, so the initial squeezing parameter R, if it's less, is mod R is less than certain, let's call it RT, then it is a better strategy to store resource in form of squeezing. Otherwise, it is a better strategy to store resource in form of entanglement. That similar thing is happening. So if if you are just below this R, then maybe it's a better strategy to store in form of entanglement. If you are above R, then maybe it is a better strategy to store. So so depending upon the initial squeezing, the better strategy is it to store resource completely in squeezing form or to store it partially in entanglement form. So that's the initial squeezing. And again, this diagram shows the scenarios. So if R is then critical value, then it is a better strategy to store in entangled form. If R is above that value, then it is a better strategy to store in the entanglement form. In this case, it is a better strategy to store in separable form, because you see the entanglement depth is larger than the entanglement. So, okay, so these all results could be summarized in this table. So you can see, so depending on the type of dissipative environment, whether you have local paths or you have single path or you have global path, and depending upon the initial squeezing, your result, whether which one of the would change, and it flips in case from local to the global path. So if R is less than some critical value, entanglement is better in single path. But in case of global path, if R is greater than some critical value, then squeezing is better than entanglement. To summarize, so we compared the robustness of squeezing and entanglement resources in two-mode Gaussian state in different dissipative environments. We consider the two different cases. First case, two-mode separable squeeze states are led to evolve in dissipative environment, and the entangled and then entangled later using some passive operation. In second case, so we're essentially passing the through a beam splitter. In the second case, the squeeze modes are first entangled using passive are allowed to evolve in a dissipative environment. So the result shows that the robustness of squeezing
Rishabh, I think we've lost you.
Yeah, I think we have lost Rishabh. He was almost done, but still we need him for the question answers. We'll wait a little. Well, I could see that he was almost done with his talk. If he joins back,
hello,
we'll wait
hello,
30 seconds.
hello.
Rishabh is here. Okay, great.
Can you?
Yes,
Yeah, so I
Rishabh is
didn't realize when the connection got off. So I didn't know where I. So was I at the summary slide?
when you were at the table.
Okay, at the table. Okay.
Yeah, the table.
Okay. Yeah, sorry for bad internet connection. So yeah. So this table sort of summarizes all these scenarios which we have discussed in this talk. So depending upon the kind of the dissipative environment, whether it's identical local bath or a single local bath or a global bath, and the condition of the amount of initial squeezing, the better strategy would change. So and it flips in the case of single local bath and global bath. So for example, if your initial squeezing is less than some critical value, then in case of single local bath, entanglement is a better strategy. But in case of global bath, if it is less than some critical value, now these critical values are different, but the essential idea is that there exists some critical value, and if it is less than that critical value, then the squeezing is better in global bath, whereas it is opposite in the single local bath. And so summary. So we compared the robustness of squeezing and entanglement resources in the two-mode Gaussian state in different dissipative environments. So we considered two cases. In the first case, we delayed the entanglement, and we let the separable squeeze state to evolve in the dissipative environment, and then we entangle them later using a beam splitter. And then in the second case, we first entangled them using a beam splitter and then allowed them to evolve in a dissipative environment. And we found that the result of the robustness of squeezing or the entanglement depends on the initial squeezing of the state and the nature of the dissipative environment. So the fact that the interconversion of squeezing and entanglement can be made just using beam splitter makes it convenient to save resource in one or the other form, and that which one is better, that depends upon the nature of the bath and the initial squeezing. So thank you. Hello.
Have we, Rishabh, are you done?
Yes, yes.
Okay, great. So the session is now open for discussion. If anybody has a question, can raise their hands. At the moment, I do not. There is a Shikhar Arora has a hand raised. Shikhar, you can unmute yourself and go ahead.
Hi, Rishabh.
Hello.
Hello. Yes. Can you hear me? Yeah. So, first of all, a nice talk. I had one doubt that you compared squeezing and entanglement. But suppose I want an ensemble of two mode squeezed vacuum state somewhere and they'll pass through a thermal bath. Which is better, the local thermal bath or the global thermal bath?
So the idea that it is so it is not in your hand to choose which kind of bath there is. So it would depend upon the kind of experiment you are doing. So the bath is sort of imposed on you. Now depending upon the bath, now we wanted to answer the question that is it better to delay the entanglement or just to make the entangled state right away at the start. So
okay. Anyways, so out of the two graphs, where did you get basically more entanglement? So okay, it's the whole spectra. Well, yes, I got the answer. Okay, yeah. So it's not in the, yeah. Thanks.
Yeah. I don't see any other questions. So let's thank the speaker, and we also close today's session. And also,
thank you.
I would like to thank both the speakers of the session and the entire day. And tomorrow we have the last day of the conference. So I expect to see people again tomorrow morning. Okay, thank you. Bye. Good night. I know it's early morning for Rishabh, but it's late evening.
I'm still in India, sir. So the visa is still.
Oh, you're still around.
Okay. No. So the thing are going online, and so they have just opened the biometric center now, and I have a biometric appointment on 15th. So maybe next month.
All right. Okay then. So thank you very much. We formally close this session. Bye.